Hi everyone, hope you all doing great. Hope you all preparing well. So today we are going to discuss GTQ program of DBMS for the GATE 2024 for GATE Computer Science and GATE Data Science and Artificial Intelligence DA batch. Okay, this is the common subject for GATE Computer Science as well as GATE DA. Approximately 2 hours duration, and we'll try to cover maximum model questions based on the last few years, whatever the areas they use it to ask, and what are the probable areas which we can able to expect this year. All we going to see in this session. So you also please try to solve the problem before taking the solution, and note down the question, and please be ready with the pen and paper, and on and when the question is displayed, and pause the video for some time and solve the question. Okay, so I'm trying to cover all most important areas and most probable areas related to the GATE Computer Science and GATE DA papers. Okay, let's move to the first question. This question related to finding number of super keys. So this is the one model question which given multiple times in the PYQs. Okay, so consider given relational schema A, B, C, D, E, F, G, H, total 8 attributes with candidate keys, 4 candidate keys A, B, C, D and E, and how many super keys in the relation. Okay, so the number of super keys of the given relational schema. Number of super keys of relation R equal to, you can compute like this: number of super keys among prime attributes of relation R multiplied with 2 power number of non-prime attributes of relation R. So like this we can compute the total possible super keys of the relational schema. Total possible super keys of the relational schema, okay, is number of super keys among all the prime attributes of the relation multiplied with 2 power number of non-prime attributes. Okay, so these are the 4 candidate keys given. These are the 4 candidate keys given. So attributes which belongs to candidate keys are the prime attributes. Okay, attributes which belongs to candidate keys are the prime attributes. So A, B, C, D, E are the prime attributes. F, G, H, C, D, F, G, H, okay, is the non-prime attributes. Okay, now among these prime attributes, so these are the candidate keys given. So A one candidate key, BC is one other candidate key, and attribute D is one candidate key, and attribute E is the one candidate key. So these are the 4 candidate keys given. Now we need to compute the super keys among these 5 attributes, A, B, C, D, E, right? Super keys among these 5 attributes A, B, C, D, E. Okay, so A and D and E are the simple keys. Okay, A combined with any other attribute. Okay, A combined with 0 or more attributes of B, C, D, E is a super key. D combined with any subset of A, B, C, E is also super key. E combined with any subset of A, D, C, A, B, C, D is also super keys. Okay, but only B not a candidate key means not a super key. Okay, only C not a super key. Okay, so total these are 5 prime attributes. So 5 prime attributes means 2 power 5 subsets. 2 power 5 subsets including empty set. So we are finding number of super keys among prime. Number of super keys. So among prime first. among prime attributes of the relation. Out of 2 power 5 subsets, one subset is not super key, which is empty set. Okay, empty set is also is one of the subset among 2 power 5. So this is definitely not a super key. Okay, I am excluded that possibility. That means 2 power 5 minus 1. So out of remaining non-empty subsets, so because BC combinedly candidate key, only B and only C is not a candidate key, not a super keys also. Okay, so that means those are the two possibilities which are not super keys. Also subtracting two possibilities. What are those two possibilities? Only B is not a super key, only C is not a super key. Okay, only B and only C is not super keys, not candidate keys also, as well as not super keys also. We are excluded those two possibilities. Other than these three, other than empty set and other than only B and only C, because A combined with A itself is super key, A combined with any other attribute also super key, D itself is super key, D combined with any attribute is also super key, E combined with any other attribute also super key. If you take any attributes of 2, if you take any attributes of 2 among A, B, D, E is also super key. So definitely 3 attributes, every possible 3 attributes is super key. Only attributes of the prime which are not super keys, empty set is not super key, and only B not super key, only C not super key. 3 possibilities excluded. So these are total 32 minus 3. 32 minus 3 is, okay, so 29. So 29 super keys among the prime attributes. Okay. So now the total number of super keys, is total number of super keys among the prime attributes, which is 29. Okay, multiplied with 2 power number of non-prime attributes. So number of non-prime attributes are E, F, G, H, 3 non-prime attributes, right? There, right? So 29 multiplied with 2 cube is the total number of super keys. That means 29, so multiplied with 8 super keys. Okay, so for total number of super keys. So total super keys of the given relational schema is 232. Now see how it is working correctly. Okay, so for example, so super keys of the relational schema means super keys of the prime attributes also. Okay, so among the super keys of prime attributes, okay, if you take any super key of the prime attribute, for example, A is one of the prime attribute which is super key. A combined with any subset of F, G, H, A combined with, for one super key, if you add 0 or more any other attributes, it remains super key only. Okay, so for each of the super key among the prime attribute, you can add 0 or more non-prime attributes also. That attribute set remains super key. For example, BC is one of the super key among the prime attribute. BC combined with any subset of other attributes is also super key. So for example, AD also one of the super key. AD combinedly not a candidate key, not only AD, AB, AC, AD, AE, like that. Okay, these are also attributes, 2 attributes is a super key. Okay, AB is one super key. AB combined with any subset of non-prime attributes is also super key. Is this clear? So this is the way we can calculate number of super keys of the relational schema is number of super keys among the prime attributes multiplied with 2 power number of non-prime attributes. Okay, this method is better if you are able to compute, total number of super keys of the prime, okay, in less time. Okay, so that means not much time required to find number of super keys among the prime, because total 5 attributes is a prime attributes, 2 power 5 subsets, empty set is not super key. Okay, so these are the 3 simple keys. Those 3 simple keys, if you combine with any attribute, is remain super key only, and BC combinedly one candidate key, means BC combined with other attributes is super key, but only B, only C is not a super key. Even A combined with B, C combined with D, A combined with B combined with D, and C combined with E, those also super keys. Only excluded part, only B not a super key, only C not a super key. Okay, so BC combinedly one super key and BC combined with any other attribute is also super key. So that means it is not much difficult to compute the number of super keys among the prime attribute. Simply multiply 2 power number of non-prime attributes, right? See this question, this is multiple choice question. Okay, multiple choice question, again finding number of super keys. Okay, so see, total 4 candidate keys are given, 4 candidate keys are given. Out of the 2 simple keys, 2 compound keys, total n attributes. Assume that n is bigger than equal to 5. Okay, so that means number of attributes are more than the attributes of the prime. Assume that. Okay, so the number of super keys of the given relational schema, number of super keys of relation R equal to number of super keys among the prime attributes, number of super keys among prime attributes of relation multiplied with 2 power number of non-prime attributes. Non-prime attributes of the relation R. Okay, each of the super key among the prime attribute, if you combine any subset of non-prime attribute, it remains the super key only. In this way, we can calculate total number of super keys. Okay, so now we need to calculate the number of super keys among the prime attributes. So number of super keys among the prime attributes, number of super keys among prime attributes of relation R. Okay, so these are the candidate keys given, minimal super keys, or we can say candidate keys. These are the candidate keys given. So A1 is one candidate key, A2 is one candidate key, and A3, A4 is one other candidate key, and A5, A6, A4, A5 is the other candidate key. Total 4 candidate keys which involved 5 attributes. Okay, so now, to get the total super keys among the prime attributes, 5 attributes are prime attributes, 5 attributes are prime attributes, 2 power 5 subsets. Okay, from this eliminate subsets which are not super keys. Okay, because we want super keys among the prime. So not every subset of 5 attributes is a super key. So eliminate subsets which are not not super keys. Okay, so obviously one possibility, empty set, empty set is also one of the subset among these 2 power 5 subsets. Empty set, okay, is also one of the subset among the 5 attributes of the prime. Okay, which is not super key, excluded that possibility. And not only empty set, see, if you take the 1 attribute, only A1 super key, only A2 super key, but only A3, only A4, only A5 is not super keys. Okay, so only A3 is not super key, only A4 is not super key, only A5 is not super key. Okay, only A1 and only A2, okay, are super keys because those are simple candidate keys. Okay, candidate keys is also super keys. Okay, so these are the 3 possibilities which are not super keys eliminated, subtracting from the all subsets. Okay, so if you take any possibility of 2 attributes, is there any 2 attributes possibility among these prime attributes which is not super key? So A1 combined with any of the other attribute of the prime is also super key. A2 is a candidate key, means A2 combined with any of the other attribute among these 5 attributes, okay, is also super key, right? So that means 2 attributes possibility which involved A1, A2 is also super keys, and 2 attributes A3, A4 also super key, A4, A5 also super key. But this subset which has 2 attributes, A3 and A5, okay, only A3 is not super key, only A5 is not super key, A3, A5 combinedly not super key. Okay, this is one of the subset which is 2 attribute selection, not super key, right? but A3 combined with A4 super key and A4 combined with A5 super key, like that. Remaining 2 attribute selection is a super key only. So this is one of the subset of 2 attributes, which is not super key. We are eliminating the possibilities of not super keys. Okay. So we are eliminating this one possibility. If you take any of the 3 attribute selection, A1 with other 2 attributes, A2 with other 2 attributes, A3, A4 with other 2 attributes, A4, A5 with other 2 attributes, even A3, A5 with other attribute. A3, A5 means which are, A3, A5 is not super key. But if you take 3 attributes along with A3, A5, okay, so A3, A5, you can take A4, that is also super key. A3, A5, we can take A2, that is also super key. A3, A5, we can take A1, that is also super key. So means say every possibility of 3 attribute selection, among these 5 prime attributes is also super keys. Obviously 4 attribute selection is also super key. All 5 prime attributes combinedly also super key. Only these are the 4 possibilities from 2 power 5 subsets of the prime, okay, so is not a super keys, okay. So 4 or 5 possibilities. So 32 minus 5, that means 27 super keys among the prime attributes, okay. So total 27 super keys among the prime attributes. If total 27 super keys among the prime attributes, total number of super keys are among the prime attributes multiplied with 2 power number of non-prime attributes. N attributes, out of that 5 attributes are the prime, non-prime attributes are n minus 5. So this is the total number of super keys of the given relational schema. So answer to this question is C, right. So this is the way we can compute the number of super keys of the given relational schema. See this one. This is also question related to find number of super keys, okay, but here less number of candidate keys and more prime attributes. Only 3 candidate keys and 5 prime attributes, okay. So in such cases we can go for set theory representation for finding number of super keys, because only super keys of the first set, super keys of the second set, super keys of the third set. Okay, super keys because of first candidate key, super keys because of second candidate key, super keys because of third candidate key. Only 3 sets are there, so we can perform union for them. It is become much easier, right? So now, so we can also compute the number of super keys like this. These are the super keys because of first candidate key, and super keys because of second candidate key, and super keys because of third candidate key. Okay. So the first candidate key having 2 attributes, A1, A2, okay. Second candidate key is 2 attributes, A3, A4, and third candidate key 2 attributes, A4, A5. Now, so total n attributes in the relational schema. So A1, A2, 1 candidate key means A1, A2 combined with any subset of remaining attributes. A1, A2 combined with any subset of remaining attributes is also super keys. That means it becomes 2 power n minus 2 super keys because of this first candidate key. Okay, these are the total number of super keys. So total number of super keys because of candidate key A1, A2. Okay. Similarly, 2 power n minus 2 super keys because of second candidate key, 2 power n minus 2 super keys because of third candidate key. Okay. And this intersection super keys, okay, this intersection super keys which are because of A1, A2, A3, A4 common attributes. A1, A2, A3, A4 is one of the super keys, So super keys which common for these 2 sets. So total 4 attributes combined with any subset of remaining attributes becomes this common super key. That means this becomes 2 power n minus 4 super keys. Okay. This second and third set, the second and third set. So A3, A4, A5. A3, A4, A5. Okay, so combined with any subset of remaining attributes. Okay, so 2 power n minus 3 super keys. Okay, so this intersection A1, A2, A4, A5. A1, A2, A4, A5. This is 2 power n minus 4 super keys. Okay, so then common super keys of all the 3 sets. Common super keys of all the 3 sets, total 5 attributes. So which is A1, A2, A3, A4, A5. So combined with subset of other attributes is 2 power n minus 5 super keys. Okay, so let's assume that this 2 power n minus 2 super keys is one set. This 2 power n minus 2 super keys is second set. This 2 power n minus 2 super keys is the third set. Okay, we need to compute total super keys of the union of 3 sets. So number of super keys of X union, Y union, Z set. Okay, which is equal to number of super keys of the first set plus number of super keys of the second set plus number of super keys of the third set minus number of super keys of X intersection Y minus number of super keys of X intersection Z minus number of super keys of Y intersection Z. Okay, so plus number of super keys of X intersection Y intersection Z. Okay, so just we need to compute the total value. So super keys of the first set 2 power n minus 2 and super keys of the second set 2 power n minus 2 and super keys of the third set 2 power n minus 2 minus super keys of first and second set intersection 2 power n minus 4. Super keys of first and third set intersection is also 2 power n minus 4. Okay, minus super keys of second and third YZ intersection is 2 power n minus 3 plus super keys of all the 3 sets 2 power n minus 5. So minus 2 power n minus 4 minus 2 power n minus 4. Okay, so is become minus 2 power n minus 3. These two minus 2 power n minus 3 minus 2 power n minus 3 minus 2 power n minus 3 is minus 2 power n minus 2. That means 1 plus 2 power n minus 2 and these 3 negative values get cancelled. This summation is become minus 2 power n minus 2 plus 2 power n minus 2 get cancelled. So remaining possibilities, if 2 power n minus 5 common, smaller term 2 power n minus 5 is common, then 2 cube plus 2 cube plus 1. Okay, so 8 plus 8 plus 1, 17. So total 17 multiplied with 2 power n minus 5 super keys. Right? See this question, one more question, and this model also very frequent in the examination. And consider given relational schema A, B, C, D, E, F, G, and with functional dependencies are given. How many candidate keys, total how many candidate keys in the given relational schema? So the question from the normalization. So from last 2-3 years at almost they are giving. Okay, so 2 questions from normalization. So we should not ignore the normalization question, even though it is one of the frequent model question, right? So please practice, please solve the question once. Okay, so functional dependencies are given. A, B determines C, C determines D, C, D determines A, E, D, E determines F, and E, F determines G, and F, G determines B. We need to find total number of candidate keys of the given relational schema. So first we need to find one candidate key. So then from that we can able to get the what are other possibilities of candidate key. So AB determines the C, C determines the D, CD also determines the E, DE also determines the F, EF also determines the G, and so AB closure is determining all attributes. Okay, AB closure determining all attributes, that is A, B, C, D, E, F, G, all 7 attributes, right? So AB is super key, C proper subset of AB is super key or not. Okay, so the minimal super key means, minimal super key or a candidate key means, okay, this is the definition. Okay, so I'm just displaying for reference purpose. So just go through the definition once. So candidate key of the relational schema or minimal super key of the relational schema. X is candidate key of relational schema or if and only if that X must be super key of the relation. Okay, X must be super key of the relation. Okay, it means X closure should determine all attributes. The proper subset of X, proper subset of X is super key of the relation. No proper subset of X should be a super key of the relation. X should be super key, the proper subset of X should not be a super key. So that kind of attribute set X can considered as minimal super key or candidate key. So AB is super key because AB closure determines all the attributes of relational schema. So proper subset of AB, proper subset of AB is A closure is only A as well as B closure is only B. Okay, A not super key, B not super key. So AB is one of the candidate key. So AB is one of the candidate key of this given relational schema. Okay, so A and B are the prime attributes. Okay, A is a prime attribute of the relation and B is also prime attribute of the relation because AB is candidate key. If any non-trivial FD, X determines Y, okay, with determiner is a prime attribute. With determiner is a prime attribute. If this kind of non-trivial FD exists, okay, then more than one candidate key exists. Okay, if no non-trivial FD whose determiner is a prime, no non-trivial FD whose determiner is a prime, then for such a relation one candidate key only. Okay, any of the non-trivial FD whose determiner is right side attribute set is prime, then more than one candidate key possible, right? So this A determined by ZD, okay, so A determined by CD, A is also prime, B determined by FG, B is also prime. So if you observe, this B is a prime attribute. Okay, this B is a prime attribute which is determined by, this B is a prime attribute which is determined by FG. Okay, see, AB determines all attributes, AB determines all attributes. Okay, FG determines the B, FG determines the B. So if AB determines all attributes, FG determines the B, B determined by FG, it means that AFG also determines all attributes. AFG also determines all attributes. Okay, that is what the pseudo transitive rule, right? So for example, if AB determines the C, okay, AB determines the C, or we can say XY determines Z. Okay, XY determines Z. Assume that this Y itself is determined by W. Okay, W determines the Y. XY determines the Z, W determines the Y. So according to pseudo transitive rule, because Y is determined by W, so XW also determines the Z. Okay, Y determined by W, in place of Y you can take the W. XW also determines the Z. So this is the pseudo transitive rule, okay, over the FDs. Okay, similarly, AB determines all these attributes, FG determines this B. Okay, that means B determines by FG. So in place of B, if you take this FG, AFG also determines all attributes. So A, B, C, D, E, F, G. Now Now see, is it minimal super key or not? Okay, so to test minimal super key or not, A of G should be super key, that is already proved. Okay, proper subset of A of G should not be a super key. So no need to take all the proper subset closure. So this having 3 attributes, na, you can test 2 attribute closures, because if AF closure, FG closure, AG closure, in case not determined all attributes, definitely only A closure, only F closure, only G closure also not determines all attributes, right? So now the subset closure we are testing. So AF closure is only AF for the above FD set. Okay, so FG closure determines B also, FGB, but still not super key, not determines remaining attributes. Okay, so only AF not super key, only FG not super key. AZ closure for above FD set is only AZ. Okay, so AFG determines all attributes, but proper subset of AFG not determining all attributes. So we can say this AFG is one other candidate key. AFG is one other candidate key. It means that F and G also prime attributes. F also prime attribute, G also prime attribute. If any prime attribute determined by other attribute set, okay, so then also we can have other candidate key. So because G is a prime attribute, which is determined by EF. Okay, see here AFG determines all attributes, EF determines the G. AFG determines ABCD EFG, EF determines the G, that means G determined by EF. Okay, in place of this G, if you take this FG, okay, in place of this G, if you take this FG like a pseudo transitivity, okay, that means AEF also determines all attributes. Okay, so AEF also determines all attributes. AEF closure determines A, B, C, D, E, F, G. Again see, proper subset of AFG determining all attributes or not. So now AF closure already calculated. So test AE closure and EF closure. Okay, so at most 3 attributes is the super key. To test minimal or not, sufficient to calculate at most 2 attribute closures. Okay, so AE closure is only AE not determining any other attribute by using above FD set. EF closure determines EFGB. EF closure determines EF as well as G and B. F is a prime attribute. F is determined by DE. F is a prime attribute. F is determined by DE. Okay, so F is there in 2 keys. F can replace by the DE. Okay, so in AFG, F is replaced with the DE. It becomes ADEG. Then other one is AEF. This F is replaced with the DE. Okay, it becomes ADE. So anyhow ADE is subset of ADEG. So ADEG definitely not minimal. Okay, so the possibility of next minimal super key, that is ADE. ADE closure also guaranteed determines all attributes. A, B, C, D, E, F, G. Okay, because AEF determines all attributes and DE determines F. Okay, according to pseudo transitivity, because F determined by DE, so this F if replaced with the DE, then whatever AEF closure is occurs, okay, ADE closure also determines those attributes. Okay, again see, this is minimal super key or not. Again check this one, minimal super key or not. So AD closure, what are proper subsets we need to calculate? So AD closure, okay, DE closure, AE closure already tested, which is not super key. AD closure for above FD set is only AD. and DE closure for above FD set DEFGB. DEFGB. Okay. So still DE not a candidate key, not a minimal super key, not a super key also. Okay. So AD not super key, DE not super key, AE not super key. That means ADE is become one other candidate key. ADE is become one other candidate key. It means that so D also prime attribute. D also prime attribute, and A and E is there in both the keys. Okay, this AEF also AE is there, and ADE is also AE is there. So combinedly we can consider this AE. This AE is a prime attribute which determined by the CD. Okay, so this AE replaced by the CD. This AE replaced by the CD, it becomes CD. This AE replaced by the CD, it becomes CDF. CDF definitely not minimal because CD is super key. Okay, so because of CD determines AF, because of CD determines AE. Okay, so AE is determined by the CD. So this AE can replace by the CD. Overall, it becomes CD. Okay, CD closure also determines all attributes, which is A, B, C, D, E, F, G. Okay, so we already proved AB is one of the candidate key, and AEF is one of the candidate key, and AEF is also candidate key, and ADE is also candidate key. Now we got the CD. Okay, CD closure determines all attributes. CD is minimal or not. Okay, to test minimal super key or not, so we need to take single attribute closure. So only C closure if we calculate. C closure is CD, and CD determines AE, CD determines AE, D determines F, G, B. Okay, D determines F as well as G and B. That means not only CD closure, okay, C closure also determines all attributes. It means that CD is super key but not candidate key. CD is super key but not candidate key. So C is become candidate key. Okay, C is become candidate key. So another candidate key is C. Okay, so C is the one more candidate key. Okay, so D is also prime attribute, C is also prime attribute, as well as D is also prime attribute. This FD tested, these all FDs are done. Okay, in place of this prime attribute D of the previous key, if you replace with the C, so what is candidate key where D is a prime attribute? So this second candidate key. Okay, this one, this candidate key ADE. In place of D, if you replace with the C, it become ACE. Okay, so in this ADE, D is a prime attribute determined by the C. If you replace C, okay, this become ACE. ACE is not minimal super key because C is already a candidate key. Okay, so now this also done, and C is a prime attribute, is there in one of the key. C replaced by AB, then again we are getting the same first candidate key. So no more possibility of candidate keys. So total 5 candidate keys in this given relational schema. Okay, total 5 candidate keys. So finding candidate key of the given relational schema is NP complete problem according to the procedure. Finding candidate key of the given relational schema is NPC problem, exponential time complexity problem. So if more FDs are given, more complicated FDs are given, it may take little more calculations also to decide all number of candidate keys. Okay, but examination question in average difficulty level they use it to ask to find the candidate keys. Okay, if too many attributes are given, 16 17 attributes are given. Okay, so many random FDs are given, okay, like not in one proper sequence FD like this, so many random FDs are given. Okay, So then definitely it takes lot of time to find the all candidate keys of the given relational schema, because finding candidate key of the given relational schema is NP complete problem, exponential time complexity problem. Okay, if more complicated FDs are given and more attributes in the relational schema, definitely takes little more calculation, but examination point of view, so 6 attributes, 7 attributes, some 6-7 functional dependencies, that level, medium level question is possible for the GATE exam, right? See this question, one other question from the normalization, which of the following given statement is or true? If relation schema R is in 3NF, first statement, if relational schema R is in 3NF, okay, and all simple candidate keys, okay, so means all the candidate keys of the relation is simple candidate keys, no composite candidate key, then relation R also in BCNF, okay. See, whenever already 3NF is true, means no partial dependency, okay, no partial dependency, because already satisfied the third normal form, proper subset of candidate key determines non-prime, definitely not there, okay, because 3NF is true, and non-prime determines some other non-prime, attribute determines some other non-prime is also not there, because if those FDs partial dependency or non-prime determines one other non-prime attribute, if those FDs are there, it will fail 3NF, but he is saying that relation is in 3NF, okay. So then 2, already it is 3NF, now the question is, it is possible, it is in BCNF or not, okay. So whenever we say, see for example, if relation R is 3NF, relation R 3NF, okay, but not BCNF, assume that, but not BCNF, okay, this scenario is possible, if okay, proper subset of candidate key, okay, proper subset of candidate key determines proper subset of some other candidate key, proper subset of other candidate key. This kind of FD must exist in the relation R, must exist in relation R, okay. 3NF but not BCNF, 3NF, okay, but not BCNF. It means that is a difference between 3NF and BCNF, okay. This kind of FD allowed for the 3NF because, okay, so the left side not a super key but right side is a prime attribute, okay. So allowed by the 3NF because left side not a super key for this FD, it is not allowed for BCNF, okay. Whenever 3NF is true and BCNF is false, this kind of FD should exist. This kind of FD is possible, because one proper subset of key determining other proper subset of key. This kind of FD is possible only if at least 2 compound keys, only if at least 2 compound keys. Compound, or we can say composite. Composite candidate key means 2 or more attributes forms the key, okay. So like assume that, okay, there is one candidate key AB, and some other candidate key BC, okay. So this kind of candidate keys are called composite candidate key, 2 attributes forms the key, okay. Then there is a possibility that, this proper subset of key A can determine this proper subset of key C, or this proper subset of key C can determine this proper subset of A, is may possible in the relation, okay. So to form this proper subset of key determines proper subset of other key. So, two composite keys mandatory. Okay. So, if only one composite key is there or all simple keys are there, if only one composite key is there, all simple keys are there, then this kind of FD not possible. In case, okay, in case if 3NF true, okay, if relation R in 3NF and this kind of FD not exist, okay, assume that, okay, proper subset of candidate key, proper subset of candidate key determines proper subset of other candidate key, proper subset of other candidate key. Let us say this kind of FD already 3NF, but this kind of FD, the second kind of FD, assume not exists in relation, okay, not exists in relation R, okay. So, 3NF is true and this kind of functional dependency not exist in the relation, okay. Then no other possibility that where BCNF can fail, because already satisfied 3NF, already no partial dependency, already no non-prime to non-prime dependency. This kind of dependency can fail for 3NF. We are saying that that is also not exist. Then we can say relation in BCNF also. Okay, relation in BCNF also. Okay, so because of all simple keys, okay, this kind of FD, proper subset of key determines proper subset of other key, this kind of FD is not possible and relation already in 3NF, okay. So, that means the relation guaranteed for BCNF also. The first statement is true. It is multiple selection question, MSQ question, okay. If relational schema R is in 3NF and at most one compound key, even if at most one compound key, still this kind of FD not possible, okay, at most one compound key, still this kind of FD not possible, okay. So, still proper subset of key determines proper subset of other key, this kind of FD not possible and it is already in 3NF. So, such a relation guaranteed for BCNF also. The second statement is also true, okay. A relational schema is 3NF, third one, and at most two composite keys, okay, compound or composite, okay. So, compound candidate key or we can say composite candidate key, okay, at most two composite candidate keys. If at most two composite candidate keys, there is a chance that proper subset of key determines proper subset of other key. In that case, it may fail for BCNF, not guaranteed for BCNF. Otherwise, we can't say guaranteed fail for BCNF also, because, okay, so to have this kind of FD, two composite keys are required. That doesn't mean that two composite keys are there, guaranteed proper subset of key determines proper subset of other key. Reversal of this statement is not true, okay. So, to form this FD, two composite candidate key mandatory, but if two composite candidate keys are there, may not have this FD also or may have that FD. So, in this case, may be in 3NF or may not be in 3NF, but he is saying that guaranteed in 3NF is false, okay. The third statement is false, okay. Relational schema R is in 3NF but not BCNF, okay, 3NF but not BCNF. So, 3NF but not BCNF means proper subset of key determines proper subset of other key should exist, okay. So, something like this one, assume relation ABC, okay, relation ABC, one of the functional dependency AB determines C, other functional dependency C determines A. Now, AB is one candidate key, A can replace with the C, BC is other candidate key. Now, see this one. So, it is 3NF, all are prime attribute and the AB is super key and A is a prime attribute, okay, 3NF. It is not BCNF, okay. Whenever 3NF but not BCNF, whenever 3NF but not BCNF, because C determines A failed for BCNF, means guaranteed proper subset of key determines proper subset of other candidate key, this kind of FDs exist, Okay, so 3n of but not BCn of means this kind of FDs exist. One proper subset of key C determines other proper subset of key. It means there is a overlapped key also. B is common. B is common. Not only two composite keys, overlapped candidate keys also. Okay. So the other possible statement for 3n of and not BCn of. Okay. Overlapped candidate key must exist. Okay. So 3n of but not BCn of, then relation must have overlapped candidate key also. Okay. So because proper subset of key determines proper subset of other key is only possible with two composite keys which are overlapped. Okay. But two composite keys which are overlapped doesn't mean that proper subset of key determines proper subset of other key mandatory. But whenever proper subset of key determines proper subset of other keys exist, then guaranteed for at least two composite keys and guaranteed for two overlapped, those two are overlapped keys. Okay, right? So must have overlapped key is also true statement. Okay, so A, B, D are the correct statements. So answer to this question A, B and D. Right, too much information in this question. So then the related one conclusion also you can consider. It is helps you to solve these kind of problems. Whenever non-trivial FDs which forms redundancy, whenever non-trivial FD which forms redundancy, X determines Y, non-trivial FD which is forms redundancy. It means X determines Y non-trivial FD with X is not super key. With X is not super key. This kind of FD which is causes the redundancy. Okay. FD forms redundancy means it failed for higher normal form. Okay. So redundancy. Such a FD exists means definitely not BCn of redundancies exist. Okay. So these are the four possibilities. These are the four possibilities FD which can cause the redundancy. Proper subset of candidate key determines non-prime. This also called partial dependency. Okay, proper subset of candidate key is determines non-prime. It is also called partial dependency. Okay, and non-prime determines other non-prime attribute, and so proper subset of key along with the non-prime may determines other non-prime attribute. Proper subset of one key determines proper subset of other key. These are the different possibilities of functional dependencies. These are the different possibilities of functional dependencies which can form the redundancy. Okay. So now this fifth one is not for FD. This is for MVD. Multi-value dependency. These are for FDs which forms redundancy. Okay. If there exists non-trivial multi-value dependency, if there exists non-trivial multi-value dependency with X is not super key, also forms redundancy. Okay. So there is no restriction for the first normal form. First normal form allowed every form of the redundancy. That's why we say more redundancy possible in the 1n of. Okay. When it comes to 2n of, this first kind of FDs is not allowed. Partial dependency we call, proper subset of key determines non-prime, but remaining form of the FDs which causes redundancy is allowed, and MVD redundancy also allowed. Okay, 3n of not allowed first three possibilities of FDs which are causes redundancy, but this FD proper subset of key determines proper subset of other key. This FD which causes redundancy is allowed here, and allowed multi-value dependency. Okay, redundancy due to multi-value dependency also. BCn of not allowed any of this kind of FD which can cause the redundancy. Any of the FD which can cause the redundancy is not allowed in BCn of. Not allowed BCn of partial dependency also. Not allowed non-prime determines other non-prime attribute also. BCn of not allowed proper subset of key along with the non-prime attributes determines some other non-prime attribute also, and BCNF not allowed this kind of FD also. But BCNF allowed non-trivial MVD which causes the redundancy. Okay, whereas fourth normal form is not allowed any form of the FD which can cause redundancy, as well as any form of the MVD which can cause the redundancy. So this is helpful to differentiate one normal form with other normal form for theoretical questions. So when it comes to difference between 1NF and 2NF, this area only. Difference between 1NF and 2NF is this area. Okay, 1NF proper subset of key determines non-prime allowed, and 2NF not allowed, remaining similarities. Okay, difference between 2NF and 3NF, difference between 2NF and 3NF is this area. Okay, so whereas in 2NF, non-prime determines some other non-prime which can cause redundancy is allowed, not allowed in 3NF. Proper subset of key combined with non-prime which determines the non-prime is allowed in 2NF, which not allowed in the 3NF, is the differences. Remaining are the similarities, allowed and both the cases, allowed both the cases, not allowed both the cases. Okay, I'm only talking about, I'm only circling the difference, not the similarity. Okay, so now the difference between 3NF and BCNF is here. Difference between 3NF and BCNF is here. Okay, 3NF allowed proper subset of key which determines proper subset of other key, means a prime attribute. Okay, BCNF is not allowed because this is also one of the non-trivial FD which can cause the redundancy, one of the non-trivial FD whose determinant is not super key. Okay, so which is allowed for the 3NF but not allowed for the BCNF. The difference between BCNF and 4NF is this one. Okay, difference is this one. So redundancy due to non-trivial MVDs is allowed in the BCNF, but redundancy due to non-trivial MVDs not allowed in the fourth normal form. Okay, so this short notes or this explanation helps to handle lot of theoretical questions, of this form. Okay, this kind of theoretical questions. See, here also indirectly we used these differences. Okay, relation is 3NF, means these first three are not there. Okay, but not BCNF, means the difference we are talking about. 3NF but not BCNF means you are thinking about difference. Proper subset of key determines proper subset of other key should exist. To have this FD, okay, at least two composite keys required. To have this FD, overlapped key required. Okay, so already 3NF only simple keys. Okay, already 3NF only simple keys. This kind of FD not possible. 3NF is true, this kind of FD not possible, then it BCNF also. 3NF is true, okay, one composite key only, then also this kind of FD not possible, then also BCNF. Okay, 3NF true, at most two composite keys are there, at least two composite keys are there. 3NF is true, at least two composite keys are there, then this kind of FD can be possible, then may fail for BCNF. Okay, so like this differences between one normal form to other normal form can be expressed much better way by using this comparison, right? So normal definitions of 2NF, 3NF, BCNF only we use while we solving the problems of highest normal form and all, but we will be handling the theoretical question related to normal form. Better use this kind of comparisons, right? Let's see one more question. This is from the Curie's relational algebra question. Okay, so consider a given relational algebra Curie and catalog relation is given, SID and supplier ID and pot ID is the primary key, pots relation is given, pot ID is the primary key. Okay, so which of the Curie correct representation to retrieve SID supplied some red or some green pot? Which is the correct representation to retrieve SIDs who supplied some red pot or some green pot? Okay, in the relational algebra, so whenever we want to access data from one relation which matches with some record or at least one record or any record of the other relation for given specification or a given condition, we use the join symbols. Okay, we use the join. So whenever we say R join S, okay, and apply the predicate condition C, okay, indirectly means that each record of the relation applies this condition. Retrieved records, okay, records of the relation which satisfy this condition with some record of other relation, okay, some record of other relation or any record of other relation or at least one record of other relation, okay, at least one record of other relation, okay. And also we can express by using cross product of two relations and apply this specific predicate condition. And if this condition is equality of common attribute, then we can go for the natural join also. If this condition is equality of common attribute, required condition. So whenever the join we used, okay, either conditional join or natural join or cross product and selection is used, okay. So mathematically those queries are, okay, retrieves the records which satisfy this condition with some record of S relation or retrieve the records of R which satisfy this condition with at least one record of this relation, okay. Mathematically we can say there exist, okay. So obviously the SIDs supplied some red pot or some green pot, supplied some red pot or some green pot, it required the join queries, right. So the pots relation, from the pots relation, so color equal to red or color equal to green pots are selected, color equal to red or color equal to green pots are selected, okay. Those pots are joins with the catalog table. So that catalog record pot ID apply predicate condition with, okay, at least one pot ID of the pots relation, at least one pot ID of the pot relation whose color equal to red or green, okay. So this is the correct query for the given specification. So one instance of catalog, one instance of pots is sufficient. Okay. Next, second query. So is also catalog table and pots table and pots table, okay. Two instances of pots relation and one instance of catalog relation is done the cross product. So catalog relation and T2 is the pots relation, T3 is also pots relation, okay. Let us see how this query works. So this catalog relation, SID pot ID, supplier who supplied the pot, cross product with the pots relation which is pot ID and color, okay, cross product with one more pots relation with pot ID and color. So these are the different attributes over the cross product result. These are the different attributes over the cross product result. So T1, T2, T3 cross product is done. Now T1 is the catalog relation, okay. This PID color is the T2 and this PID color is the T3. Then T1 PID equal to T2 PID. That means this supplier supplied pot should be equal to this pot ID, and color of this, okay, color of this T2 is red, and this pot ID is also should be equal to this pot ID, okay, and color equal to green, and it is not AND condition between them, okay. So either these two conditions should be true, either these two conditions should be true or these two conditions should be true, okay, OR operation, okay. That means that supplier supplied pot should be either red pot, otherwise that supplier supplied pot should be green pot, okay. So either this should be satisfied or this should be satisfied. Is also correct query, So because say assume that S1 who supplied the P1, and if P1 is red, let's say this assume that this is some other pot, green pot, but definitely different ID. So it is a green pot. Assume this is one of the record in cross product. Supplier who supplied this S1 P1 is same, color is red, okay. So this same pot and red pot, okay. This condition true, and obviously other condition may not be true, okay. this condition should be true or second condition should be true. So this is also correct representation. This is also correct representation for the given specification. This query also retrieves supplier who supplied either red pot or that supplier supplied pot is green pot. Okay. So the A and B both are correct representation for the given query. Then the third one, he used the catalog T1 and catalog T2, pots P1 and pots P2, and total it used 4 tables. Okay, total it used 4 tables. Okay, so it means 2 catalog instances and 2 pots instances. So that means SID pot ID is the catalog relation, and pot ID color is the pots relation. Again SID pot ID is again the this T2, okay, catalog relation, and this P2, okay, again pot ID and color. Okay, so total these are the attributes in the result of cross product. Okay, these are the attributes in the result of cross product. So cross product is done. Now see the predicate condition. T1 PID, T1 is catalog relation and P1 is pots relation. The T1 PID should be equal to P1 PID and this color equal to red. This color is red. Okay. Now, so this P1 color equal to red, these 2 conditions. Okay. Now, T2 PID is P2 PID. Okay. This T2 PID is P2 PID. This supplier has supplied the this pot, so equal, condition is equal. Okay, and these SIDs are equal is the next condition. These are all AND operation. Okay, let's remove this color equal to red condition first. Okay, so this the T1 pot ID equal to P1 pot ID, and okay, so T2 pot ID equal to P2 pot ID, and T1 SID equal to T2 SID. Right? These are the 3 conditions applied. Okay, and these are the AND operation, and with one of these conditions should be true. One of this condition should be true. Okay, one of this condition means either this pot color is red, okay, or this pot color is green. Okay, so these 2 conditions, this condition makes sure that this supplier has supplied, okay, this supplier has supplied pot, okay, and this supplier T2 is supplied the pot, and the whatever T1 SID is also equal to T2 SID for the projection purpose. For the projection purpose means, okay, what, and the color of the pot should be either red or green. Okay, so not required to satisfy both condition. Even if color equal to red is true, green false, green true, red false is also okay. So what kind of record will get satisfied here? Assume S1 who supplied the P1, and let's say P1 is of the red pot. Okay, so now this SID should be equal to this SID. Assume S1 is also supplied some P3, and this P3 is blue pot, not green, blue pot. Then the second condition is false. Even the second condition is false, still this record in the result. Okay, still this record in the result. So that supplier has supplied some red pot. Okay, so the either he supplied some red pot or he supplied some green pot. So this is also correct representation for the given query. So this query is also correct representation. See this option D. So catalog table and pots table is done the cross product. So catalog table means, so SID pot ID, supplier who supplied the pot. One more instance of catalog table, SID who supplied the pot, and pots relation PID and color. Okay, these are the attribute set in the result of cross product. after cross product, these are the attributes, right? So in order to understand these conditions, how it works, okay, let us take some sample record set. So catalog records, so assume that SID and pot ID, okay, so these are the catalog records. Let's say S1 supplied the P1, S1 also supplied the P2, and S2 supplied the P2, and S3 supplied the P3. And assume that this is the pots records. So PID and color. So P1, P2, P3, 3 pots we considered for sample data. Assume it is red pot, this is green pot, and this is blue pot. Okay, these are the pots record just for visualizing the cross product result. So cross product is done. So first T1 instance is the catalog records. The T1 instance is the catalog records, and T2 instance is also catalog record. This T2 instance also catalog records, and this is the pots records. Okay, P1 is the pots records. Actually, these are not 3 records, there are 4 records. It's a cross product result. These 4 records cross product with, I am not written in detailed all the records. 4 multiplied with 4. Okay, so 16 multiplied with 3. Those many records in the result. In between cross product, 4 multiplied with 4 multiplied with 3. Those many records. Over these many records, we are applying these conditions. Conditions T1 PID equal to P1 PID. Okay, so these pots, this pot ID should be equal, and so this pot ID P1 is this one should be equal, and this second one T2 PID equal to P1 PID. This pot ID also should be equal, and third one, these SID should be equal. Okay, those are the 3 conditions with end operation. The fourth condition, this color should be either red or green. Okay, is the fourth condition. Okay, one of these. Now see what combination it satisfies. So this P1 equal to P1, and this T1 SID equal to T1 SID, T2 PID equal to, okay, P1 PID. So this combination is one of the record which satisfy the all predicate conditions. So this S1 in the result. Okay, so the other combination S1 P1 combined with P2 green pot. So this PIDs are not equal, that is not in the result. Okay, similarly if you take this pair not satisfy with other 2 records for all the conditions. So similarly, so S1, this PID should be equal to this PID, P2 equal to P1 also false. This second record, so this P2 equal to this P2 is true, SID is same, and this P2 equal to this P2 is also true, color equal to green also true, either red or green. This pair also in the result. Okay, this S2 P2, this P2 equal to this P2, and this P2 equal to this P2, this pair also satisfy the condition. So these all records are in the result. Okay, so P3 equal to this P3 and this P3 equal to this P3, but this color is neither red or green. So this combination, okay, is fails. Okay, so S1, S2 both are in the records. This is also correct query for the given specification. Okay, this is also correct query for the given specification. Okay, so all 4 queries are correct for the given specification. So we need to retrieve SIDs who supplied some red or some green pot. So by using one instance of catalog and pots also can be expressed. By using one instance of catalog, 2 instance of pots also can be expressed. By using 2 instance of catalog and 2 instance of pots also possible to express, or by using 2 instance of catalog and 1 instance of pot is also possible to express. So answer to this question is all options. Right? the next similar question, so we need to retrieve SID supplied some red pot and some green pot. We need to retrieve SIDs who supplied some red pot as well as some green pot. So retrieve the supplier who has supplied the pot, supplier who supplied the pot should be one of the red or one of the red and one of the green. Okay, such a supplier we need. Okay, so the first query, one instance of catalog, one instance of pots is used. See, the join is works like some, any, at least one, that is okay. But see, the pot color equal to red, pot color equal to red and pot color equal to green. So these two predicate conditions not true for, not possible to satisfy for any record of the pot selection. Okay, color equal to red and color equal to green. This predicate condition applied for each individual record of the pot selection. The first record, if it is red pot, then definitely green pot, condition green is false. If it is green pot, condition red is false. Okay, so in this way, the total records which are in the result of, okay, this portion, total records in the result of this portion is empty. No record can satisfy these all predicate conditions, means say color equal to red and color equal to green condition. If empty record set, okay, empty record set is retrieved from the pot selection, means no record is the result of the selection, that is joins with the catalog table. So if it is one of the subrelation, one of the table is 0 records, if you perform natural join or conditional join, the result is also 0 records. Okay, so the output of this query is 0 tuples. Okay, always 0 tuples we can say. That means it is, even if some supplier has supplied both red and green pot, so this query not going to be retrieve such suppliers. So this is the wrong query for the given specification. This is wrong query for this given specification. Okay, so that means we can't possible to express by using one pots table to prove color equal to red and color equal to green. We can't possible to express, okay, so color equal to red and color equal to green just by using one pots table. Okay, so now the second one, here one catalog table is used, two pots tables are used. Okay, see, that means after cross product these are the records of the result. So SID, pot ID, catalog relation, pot ID color is pot selection, pot ID color is also pot selection. Okay, so this is the result of cross product. So over this cross product result, these are the predicate conditions applied. What are predicate conditions applied? T1 PID equal to T2 PID. T2 is the pots table, T1, T2, T3 all are pots table. T1 PID equal to T2 PID. And this color is red. This color is red. Then T1 PID equal to T3 PID. This T1 PID should be equal to T3 PID. And this end operation, all are end operation. This color is green. These are the predicate conditions. All conditions with the connectivity is end operation. See this one. So some supplier, assume some supplier, he has supplied some pot. Some supplier, he has supplied some pot. What we are expecting, that pot should be red pot also. That pot ID should be red pot also. That same pot ID should be green pot also. Okay, assume S1 who has supplied some pot X. That X should be red pot also, and that X should be green pot also is not possible because PID is a primary key. The ID of the red pot and ID of the green pot definitely different. Okay, if it is a pot ID is X, the pot ID is X, if it is red, okay, then this is also red, okay, because same pot. So then T3 color equal to green, T3 color equal to green, condition fails. Okay, so there is no chance that these all condition can satisfy for any record in the cross product. Okay, so for example, S1 has supplied P1, S1 has supplied P2, and S2 has supplied P2 and S3 supplied P3 is the catalog data. This is the catalog data. What is pots data? So P1 is red pot and P2 is green pot. Assume that P2 green pot and P3 is some other, neither red nor green. Let's say it's a blue pot or something. This is the pots data. Again, it's also pots relation, right? So P1 is red pot and P2 is green pot and P3 is blue pot. Okay, this is also pots data, right? So we done cross product of these three tables. Cross product of these three tables, right? Over cross product, what we are expecting, this pot ID should be equal to this pot ID, this pot ID should be also equal to this pot ID, and this should be red pot, this should be green pot. Not possible, na? For example, this first combination, if you consider this P2 color, T3 color red is false. Okay, if this combination we consider, these pot IDs are not equal. Okay, this third record combination, and obviously this pot ID is not equal and color is not green or red. Okay, so that means this S1 not matches with any of this combination. Similarly, this S1 also not matches, this S1 also not matches, this S1 also not matches. Okay, there is no chance that all these records, all these conditions true for any record of the cross product. Okay, so now 4 multiplied with 3 multiplied with 3, those many records in the cross product. Out of all the records, it can take any combination. For example, okay, this combination is also one of the cross product result. Okay, this P2 equal to this P2 is true, but this P2 equal to this P1 is false. This second condition false. So that record also not in the result. Okay, for example, if you take this combination, if you consider, so P2 equal to P1 is false, this second condition fails. T1 PID equal to T2 PID is failed. Okay, so like that, if you observe, no record of this cross product can satisfy all the conditions. So the result of this query also 0 tuples, always 0 tuples. This result is also always 0 tuples. This is also wrong query for the given specification, right? Now the third query, you just catalog T1 pots P1, catalog T2 pots P2. Okay, it uses 4 instances. Okay, so 2 instances of catalog and 2 instances of pots. Okay, so this query uses total 2 instances of catalog and 2 instances of pots. So for example, how to test this one, just check it like this. T1 is catalog, that means SID pot ID, and P1 is pots relation, that means PID and color, and T2 is catalog, that means SID and PID, and T2 is pots relation, it means PID and color. Okay, these many attributes in the result of cross product. Okay, these many attributes in the result of cross product. So then see the predicate condition. Okay, T1 PID is P1 PID, this is T1 and P1, these 2 attributes of T2, these 2 are P2. Okay, these 2 pot ID should be equal, and T2 PID equal to P2 PID, these pot ID should be equal, and T1 SID equal to T2 SID, these SIDs also should be equal, and P1 color equal to red, and P2 color equal to green. And if all these conditions are satisfied over the cross product result, okay, so that SID is retrieved. Okay, so for example, this is the catalog table. So S1 supplied P1, S1 supplied P2, and S2 supplied P2, and S3 supplied P3. These are the catalog records. Cross product with pots records. Assume P1 is red pot and P2 is green pot and P3 is blue pot. These are the pots records. Cross product with again catalog and again pots. Okay, again one more instance of catalog and pods records. Okay, so this is the combination of records in the result of cross product. It's not like these are 4 or 3 records, these are 4 multiplied with 3 multiplied with 4 multiplied with 3, those many records in the result of cross product. Now see, is there any record which can satisfy all the selection conditions? Okay, so this PID should be equal, means true for this pair. Okay, and this pot ID and this pot ID should be equal and true for this pair, and this SID should be equal to this SID. Okay, so this SID is equal to this SID, means it should be green pot, na? It should be green pot, not for this first record fails, but it can be second record. The second record can satisfy. This pair can be satisfied, color equal to green. Okay, and this PID red pot, this PID green pot, green condition, and this SID is equal to this SID. Okay, this SID is equal to this SID. If you take this combination, of record, satisfied all conditions. Okay, so similarly this combination of record. Okay, so S2 P2 is green pot, so P2 should not be a green pot. Okay, so remaining records is fails, all records is fails. Okay, so now S1 is a supplier who has supplied red pot also, who has supplied some green pot also, so remaining all records is fails. Okay, so that means S1 in the result of query who has supplied some red pot and some green pot. Okay, so indirectly this condition and these two conditions make sure that T1 catalog has supplied, this supplier has supplied some red pot. Okay, so these two conditions make sure that, so the T2 has supplied some green pot, and this condition makes sure that who has supplied red pot and also supplied green pot. Okay, so this is the correct representation for the given specification. Okay, this is the correct query. Then similarly if you observe, 2 catalog instance, 1 pods instance is given. Okay, 2 catalog instance, 1 pods instance is given. That means SID pot ID of the catalog table and SID pot ID of catalog relation, and pot ID color is the pods relation. Now see what are the different conditions. Okay, no need to run the whole query also. One pods table only used, but for 2 conditions, color equal to red and color equal to green, not possible to satisfy. Okay, so one of this condition or both of these conditions guaranteed false. Okay, even all these other predicates are true, all these conditions are true, but one of these condition guaranteed false, because if this pot color equal to red, that is guaranteed not green. If you take any record of the cross product, assume this color equal to red, then color equal to green is false, is also fails. Even if you take next record of the cross product, if it is green in case, but that is not equal to red, it is also false. Like that, no record can satisfy all these conditions, especially P1 color equal to red and P2 color equal to red. Okay, both conditions definitely not going to be true for any record of the pods relation. Okay, so this result is also 0 tuples. Okay, it is also wrong query for the given specification. Okay, so means out of these 4 given queries, to retrieve SID who supplied some red pot and some green pot, the only correct query is the third option. Okay, so the first option, 1 catalog, 1 pods, also result is 0 tuples. Okay, so the second query also result is 0 tuples, wrong query. Third query is correct query, and fourth query also 0 tuples, it's also wrong query. Okay, so to express SID who supplied at least 1 red pot to express SID who supplied at least one red pot and at least one green pot. And operation, okay, at least one, join with some red pot, join with some green pot. Okay, some means join. Okay, to express this kind of query, we need two instances. We need one instance of catalog and pot to prove that supplier has supplied some red pot. One more instance of catalog and pot to prove that supplier who supplied some green pot, and the supplier who supplied red pot and supplier who supplied green pot, those SIDs also should be equal. All conditions possible to express, all those conditions possible to express only if we have two instances of the catalog relation and two instances of the pots relation. Okay, so that's why only this query correct for above specification, right? Let's see the one more question related to the SQL queries. So which is correct query for the given specification? So enrolled relation is given, SID course ID combinedly primary key, student relation SID is a primary key, retrieve course IDs enrolled every female student, retrieve course IDs enrolled every female student. So means this is the required output. So assume there is a enrolled relation and there is a student relation, enrolled relation and student relation. So SID course ID combinedly primary key for enrolled relation and student ID is the primary key for student relation along with the gender. Okay, so assume S1, S2, S3, S4, S5 are the students. So female students as well as male students. Some sample record just to understand the question. Okay, assume there is a course which is enrolled every female. So S1, S2, S3 are the female students. Assume S1, S2, S3 are the female students. So same course C1 has enrolled all females, S1, S2, S3. Okay, may enrolled the same course by males also. Let's say C2 is the other course which has enrolled S1, S2 females and S5 is a male student, and assume C3 is enrolled by S5. So we need a course which has enrolled every female. Okay, C1 has enrolled every female, not C2 and not C3. So expected output is C1. Something like we wanted to write the SQL query. We need to find correct query to get this output. So for that, two correlated queries is given. It's a correlated query. This is inner query and this is outer query. Retrieving enrolled records where not exist. Not exist is true if inner query result is empty. If this inner query result is empty, then not exist is true. Okay. So if it is not empty, then not exist is false. The result of inner query, if it is empty, then not exist is true, then where condition is true and the corresponding course in the result. Okay, for each record of enrolled relation, outer query, okay, it computes the inner query. Okay, it computes the inner query based on result of inner query, this where clause of outer query tested. Okay, now if we assume one of the record from this enrolled relation, this is the enrolled relation as well as this is the student relation, right? So let's say this course is C1, this is the outer query table, course is C1. Okay, so we all females SIDs of the student whose gender equal to female minus, okay, students of the C1 course, all females minus students of the female course. Okay, students of the C1 course, not female course, C1 course. If result is empty, then where condition is true. Okay, see, all females minus students of one particular course, the result is empty. It means that course has enrolled every female. Okay, so that course has enrolled every female. So we are retrieving the course IDs of T1, retrieving the course IDs of T1. If exist all females minus students of that course should result should be empty. So all females are S1, S2, S3. Okay, and C1 course SIDs of the C1, SIDs of the C1 is S1, S2, S3, S4. Okay, these are the C1 student IDs. The set difference we applied. So result is empty. Result is empty means so S1 in the result. Sorry, C1 in the result. Same thing for other records as well. If you take C2, the inner query course ID is C2. T1 course ID is C2. Now all female students minus, okay, students of C2. Students of C2 is S1, S2, S5. S1, S2, S5 is the students of C2. Okay, S5. So S1, S2, S3 minus S1, S2, S5. The result is not empty. The result is S3, right? Okay, it means the C2 course not enrolled, S3 is female. Okay, C2 course not enrolled by S3 female. So that C2 course not enrolled by every female. Okay, the result if it is not empty, not exist is false. So these records are not in the result. Okay, so now C3 also same thing. So all courses are S1, S2, S3. Then courses of C3 is only S5. S1, S2, S3 minus S5 not empty. Not empty means not exist is false, and this record also not in the result. Okay, so this query is correct representation. Okay, this query correct representation for, okay, so given specification. The first query is the correct query. Then see this second query. Okay, so select distinct course IDs from enrolled relation. Okay, select distinct course IDs from enrolled relation. Okay, so where not exist female student, okay, not exist for the enrollment. Okay, so it indirectly means that, so this should become empty. Okay, this should become empty. Okay, then only this not exist is true. Then only this not exist is true. It means logically no female students, no female student. Okay, no female student, and this not exist, okay, should be true. Okay, this not exist is true means that student should have enrollment. Okay, that not exist is true means the student should have enrollment. Okay, so what we are expecting, retrieving the course such that no female student, this also should be empty, this also should be empty, then only the not exist is true. Okay, no female student who is not enrolled for that course. Okay, no female student who not enrolled for the given course. Okay, no female student not enrolled for the given course. It means that every female student has enrolled for the given course. Okay, no female student left who are not enrolled for that course. Okay, so that student female student, okay, if enrolled this course, then result is become not empty. Okay, result is become not empty, then it is become, okay, false. If this is if the female student not enrolled, if the female student if the female student has enrolled the course, then this result is not empty. Not empty means not exist is true. Not empty means not exist is false. Not exist is false means that female student is not satisfy this predicate condition. Like that all the female students should fail here. All the female students should fail here. When we are removing the female student from this set, if that student has enrolled the course. Okay, so indirectly this result is empty means no female students left. No female student left who is not enrolled that course. No female student left who is not enrolled that course. Retrieving course such that not exist a female, not exist enrollment. Not exist female who is not exist enrollment. Okay, it means that the female student has enrolled for every female student has enrolled for given course. That course has enrolled by all the females. So this is also correct query for the given specification. So both query 1 and query 2 is correct for given specification, right? See this question, one more question related to the B trees. So how many possible B trees? How many possible B trees for 10 distinct keys? How many possible B trees? Numerical question for 10 distinct keys. Okay, with order P is 5. With order P is 5, which is maximum possible block pointers per node. Okay, so that means one node can capable. So maximum 5 block pointers. 5 block pointers means, okay, so 4 keys. 4 keys except root minimum. Okay, so 5 by 2 seal value of the maximum 5 by 2 seal value, minimum 3 block pointers. Minimum 3 block pointers means 2 keys, okay, per node except root. Okay, these are the number of block pointers and keys per node except root. Root can be maximum 5 block pointers and 4 keys same, but keys 1 key and 2 block pointers is allowed. Root can be 1 key and 2 block pointers is okay. So now the question is how many distinct B trees possible for 10 keys. Okay, so assume that those 10 keys are, okay, 1 2 3 4 5, okay, 6 7 8 9 10 distinct keys. Okay, so see this one. So anyhow it can't be one single level tree. It can't be one single level tree because one single level can accommodate, root node can accommodate only 4 keys. So tree should be at least 2 levels. Tree should be at least 2 levels. Okay. Now if you take the 2 level tree, okay, if you take 2 level tree, okay, so with 1 key at the root, okay, this root node also can accommodate 4 keys and 5 block pointers, but assume only 1 key at the root. 1 key at the root means it should use 2 block pointers. Okay, it should use 2 block pointers, right? So 1 block pointer pointed to 1 node and 1 block pointer pointed to 1 node. This is one possibility of 2 levels. Okay, so in this way, one node can capable maximum 4 keys. Okay, assume this node is maximum keys are there 4 keys. Okay, this node is also maximum 4 keys are there. Okay, maximum 4 keys, and this root node is become 1 key. Okay, the root node is become one of the key. Okay, so not key one of the key, 1 key. Okay, see in this way only 9 keys can accommodate, but we have 10 keys. So this is not the possible tree. This is not the possible tree. 2 levels only, but can't be 1 key at the root. Can't be 1 key at the root, because in this way we can store 9 keys only, but we have to store 10 keys. Okay, this is the not possible option. Okay, what is other possibility of option? Okay, 2 keys for the root level. Okay, so out of 4 keys, 2 keys should be accommodated at the root level. Okay, 2 keys we accommodated at the root level. Okay, it means we should use 3 block pointers. Okay, we should use 3 block pointers. Okay, each node of the second level, can accommodate at least 2 keys, at most 4 keys. Okay, so even if you take, okay, so 2 keys here, 2 to 4 keys is okay here, 2 to 4 keys is okay here, 2 to 4 keys is okay here, and here 2 keys, right? Okay, 2 keys. Okay, so now, so minimum 6 plus 2 8, and maximum 4 plus 4 plus 12 plus 2 14. Okay, so in this structure with 2 keys in the parent, minimum 8 and maximum 4 or 14 keys can be accommodated. So this is one possible tree. Okay, this has one possibility of tree. Okay, with 2 keys at the root level. Okay, so this tree is not possible choice, and this tree has a possible choice for 10 keys. Okay, now if you take 3 keys at the root level, other possible solution, if I take 3 keys at the root level, okay, if we consider 3 keys out of 4 keys capacity, okay, if we use 3 keys at the root level, 3 keys we used at the root level means we have to use the 4 block pointers. 4 block pointers means we need 4 leaf nodes. Okay, we need to accommodate the 4 leaf nodes. If you use 4 leaf nodes, even each leaf node minimum 2 keys are stored. Okay, if each leaf node minimum 2 keys, here minimum 2 keys is stored, here minimum 2 keys is stored, and here minimum 2 keys is stored, and here minimum 2 keys is stored, here it become 3 keys. Okay, so total at least it becoming 11 keys, but we have only 10 keys. So this is also not possible structure for 10 keys. Okay, so 1 level not possible, 2 level with 1 key not sufficient for 10 keys, and 2 level with 2 keys at the parent means 3 leaf nodes is a possible structure, and so 3 keys at the root level, 2 level tree is not possible. Obviously 4 keys at the root is also not possible. 4 keys means total 5 leaf nodes are required. So 5 leaf nodes, 5 twos are, okay, 10 plus root is 4 keys, total 12 minimum keys required. Okay, so then is it possible to go 3 level even if you take at least possible keys? Okay, so even if you take 3 levels, at least possibility of the keys. Okay, so to think, okay, 2 keys should be at the root level, 1 key at the root level, 2 leaf nodes, and this node should have 2 keys, this node should have 2 keys. 2 keys minimum means 3 block pointers should be used here. Okay, 3 block pointer, 2 keys minimum means, okay, 3 block pointers should be used here. Then total it becomes 6 leaf nodes. Okay, 6 leaf nodes, minimum 12 keys required. Okay, 6 leaf nodes, minimum 12 keys required. These are 2 keys. Okay, 2 keys and 1 key. Minimum internal nodes required 5 keys. So to have this 3 level structure, okay, 12 plus 5, minimum 17 keys required, but we have only 10 keys. So this is also not possible structure. Okay, so for our 10 keys and order P equal to 5, our 10 keys are order P equal to 5, we have only one possible choice. One possible choice of the node structure. In this possible choice, okay, we have to accommodate 2 keys for the root and 3 leaf nodes. Okay, so 3 leaf node, say out of 10 keys, some 2 keys goes to the root. Okay, 2 keys goes to the root. Then if 2 keys are becomes root, and remaining 8 keys are there. 8 keys we need to distribute into 3 leaf nodes. So how many ways we can distribute 8 keys into 3 leaf nodes? How many ways we can distribute 8 keys into 3 leaf nodes? These 3 leaf nodes should be distributed by 8 keys. Okay, because 2 keys required for the root node. Okay, such that at least 2 keys and at least 2 keys, at most 4 keys. Okay, what is the possibility of distribution? All 3 nodes 2 2 2 not possible. Okay, because 8 keys required. So one possible distribution 2 to 4. One possible distribution 2 to 4. Okay, other 2 to 4, 8. Other possible distribution 3 3 2. Other possible distribution 3 to 3 3 2. Total 8 keys. We are talking about only leaves. Okay, only leaf nodes. Okay, so 8 keys are left. We need to distribute 8 keys. So 2 keys 1 node, 2 keys 1 node, 4 keys 1 node, and 3 keys 1 node, 3 keys 1 node, 4 keys 1 node. Okay, 1 2 1 3 not possible, right? 1 2 1 3, and remaining 3 keys are left, that is already covered. Okay, so 2 3s, okay, 1 2 and 2 2s and 1 4. Okay, and 2 4s not possible to take because 8 keys only available. Okay, so if you take this possible choice, number of ways of distributing 3 keys, 2 keys. Okay, 3 factorial. Okay, so 3 different choices, 3 factorial. Out of that 3 repeated, divide by 2 factorial. That means 3 ways. Okay, this is the 3 ways. And if you take this distribution, okay, so 3 factorial, out of that 2 2s are repeated, divide by 2 factorial. So these are also 3 ways. Okay, that means this way of distributing 8 keys to the leaf is 3 ways. This way of distributing 8 keys to the leaf is 3 ways. Total it becomes 6 ways. So total 6 B trees possible. Answer, total 6 B trees possible for this given 10 keys with order P equal to 5. If number of keys increases, number of different choices of trees, for example this choice and this choice both are okay for given number of keys. Not only we need to see distribution and possibilities for this structure, you have to see distribution and possibilities for this structure or that structure or that structure and all, so that number of trees can be increases. Okay, so for this 10 keys, okay, so 2 level with root 1 key not possible, and 2 level with root 3 key or 4 keys not possible, 3 levels is not possible. For this 10 keys only possible choice 2 level with root is 2 keys. Okay, so root is 2 keys means here 3 3 2. Okay, so that are 3 2 3 or 2 3 3. Okay, those are 3 ways. So 2 2 4, 2 2 4 or 2 4 2 or 4 2 2, that is a 3 ways. Okay, total 6 possible bit trees for the 10 keys with order P equal to 5. So if order decreases, number of trees increases, and keys, okay, increases, also number of possibilities is increases, right? This is one important model question. So far in the GATE examination, not given this model, okay, from the B tree, B plus tree. So far in the GATE examination, this model is not given. So huge possibility is there to frame this model question, because numerical questions and counting, these kind of things much frequent in the GATE examination, right? Let's see one more question related to B plus tree. To find number of different possible B plus trees for given number of keys. So how many possible B plus trees? How many possible B plus trees for 10 distinct keys? Okay, if 10 distinct keys, how many possible B plus tree with order P is 5? Okay, with order P is 5. So order P is 5 means, so maximum 4 keys and 5 pointers. Okay, minimum, okay, 3 pointers, okay, and 2 keys. I think this capacity of the node you know, except root. Okay, this is the capacity except root. Root node can be, if it is root node is also maximum 4 keys and 5 pointers, and minimum is 1 key and 2 pointer. Okay, this is the node capacity. So because if the minimum P by 2 seal pointers, minimum P by 2 seal pointers to maximum P pointers except root node, okay, is the capacity of node, because P is given 5, right? Now we need to see for 10 and one important thing about the B plus tree, all the 10 keys which used for construction of B plus tree should be at the leaf level. All the 10 keys which we used for construction of the B plus tree should be at the leaf level. Now with this scenario of 10 keys, so what are different structures? Okay, can't be a single level tree, because if it is a single level tree, maximum 4 keys only can accommodate. So we have 10 keys. Okay, that means tree must be at least 2 levels. Okay, let us see what is that. I'm just formatting different possibilities of trees. Different possibilities of trees. For example, okay, one possibility, 1 key at the root level. If 1 key at the root level, it means 2 block pointers should be used. 1 key at the root level, it means 2 block pointers should be used. That means, so this tree can accommodate, okay, 2 keys minimum and 4 keys minimum here, maximum, 2 keys minimum and 4 keys maximum, 2 nodes. Okay, so 2 keys minimum 4 keys and 4 keys minimum maximum 8 keys. That means the range is, okay, so 4 to 8 keys can able to store. 4 to 8 keys can able to store, excluding internal node keys, because all the keys should be at the leaf level, but we have 10 keys. So for 10 keys it is not possible structure. For 10 keys it is not possible structure. So other possibility, if you take 2 keys for the root, if you take 2 keys for the root, then 3 leaf nodes, because 3 pointers should be used. 3 pointers used means 3 leaf nodes. Okay, each leaf node minimum 2 keys, maximum 4 keys. Okay, that means minimum 6 and maximum 12. Minimum 6 and maximum 12 keys can be stored in the leaf level. Okay, so we have 10 keys, so it is in the correct range only. So this is a possible structure, because all 10 keys should be at the leaf level. Internal node keys are not countable. Okay, the one of the leaf node key only stored in the internal node keys for the B plus tree. Okay, so then because we have only 10 keys, so first structure not possible, second structure is okay. Third structure, if 3 keys in the root level, okay, if 3 keys in the root level, then we need to go for 4 block pointers. 4 block pointers pointed to 4 leaf nodes. 4 block pointers pointed to 4 leaf nodes. So minimum 4 twos are, okay, so minimum 8 keys to maximum 4 fours are 16 keys. Minimum 8 keys and maximum 16 keys can be stored in this structure. Okay, it is also okay. 10 is in between this range. Okay, this also possible tree. If I take 4 keys at the root level, okay, total 4 keys if we consider for the root level, then we have to use 5 block pointers. We have to use 5 block pointers. 5 block pointers means 5 nodes at the next level. 5 nodes at the next level. So 5 twos are 10. Minimum 10 nodes, 10 keys to maximum 5 fours are 20. Right? Okay. Maximum 20 keys. Okay. So in this structure of the leaf nodes. Okay. So in this structure we can accommodate minimum 10 keys and maximum 20 keys. It is also okay, because we have 10 keys and we can accommodate in this tree also. If you take next possibility, 3 level tree. If 3 level tree. So 3 level tree, root can be 1 key. Root can be 1 key, but other than the root minimum 2 keys. Na? Other than the root minimum 2 keys. So here minimum 2 keys required. Minimum 2 keys required means 3 pointers should be used. Here also minimum 2 keys required. Minimum 2 keys required means 3 pointers should be used. These 3 pointers for 3 leaf nodes. These 3 pointers for 3 leaf nodes. Total 6 leaf nodes. 6 leaf nodes means minimum 12 keys and maximum 24 keys required. Okay, minimum 12 keys and maximum 24 keys has to be accommodated here. Okay, so this also not possible structure. Okay, this also not possible structure, because we have 10 keys only, but here minimum 12 keys are required. So out of all the different possibilities, this structure, this structure, this structure, these are the 3 possible structures for our question. Okay, these are the 3 possible structures for our question. Means 2 level with root can have, okay, 2 level with root can have, okay, 2 keys, okay, 2 level with root can have 3 keys, 2 level root can have 3 keys. Okay, so 2 level with root 1 key not possible and 3 levels also not possible. These are the possible cases. Now distribute 10 keys into the leaf level. Okay, distribute all 10 keys into the leaf level. Distribute 10 keys into leaf level. Right? Okay, 10 distinct keys is given. Now, so here what are possibilities? Minimum 2 keys, such that, okay, such that each leaf node, okay, minimum 2 keys and maximum 4 keys. Maximum 4 keys. So now what way we can distribute into the 3 leaf nodes? Okay, what is possible choices? Okay, so 2, 2, 4 not possible because 10 keys are there. Okay, so like one choice is 4, 4, 2. Okay, 3 4s are not possible. 2 4s and 1 2. Okay, 1 4 and 3 threes, 2 threes is also okay. One node 4 keys, other two nodes 3 keys. Okay, two node 4 keys, third node is 3 key. Okay, so this possible distribution. I can't take all the 3 nodes 3 keys. We can't take all the 3 nodes 4 keys because we have only 10 keys. Okay, so only these are the two choices. Okay, so if you take this choice, okay, so the 3 factorial, okay, 3 factorial ways we can distribute, divide by 2 factorial. 2 4s are repeated, na, 2 factorial. Okay, this is the 3 ways. Okay, and this is also, okay, 3 factorial because of 3 repeated 2 times. Okay, divide by 2 factorial. So this is the, okay, also 3 ways. What are those 3 ways? So first node 4 keys, second node 4 keys, third node 2 keys. Okay, are 4 2 4 or 2 4 4. Okay, for the first distribution. Okay, 4 3 3, 3 4 3, 3 3 4. Okay, total 3 ways, total 6 ways. Okay, this first structure is calculated possibilities. Now, distribute this 10 keys into the 4 leaf nodes. Distribute 10 keys into the 4 leaf nodes, minimum 2 keys and maximum 4 keys. What is choices? Okay, so 3 twos, 3 leaf nodes, 2 keys, 1 leaf node 4 keys. Okay, so 2 twos, 4 and 6 keys can be taken 3 3. Okay, so 2 4s if we consider, okay, 2 4 keys if we consider, okay, then 8 is over, remaining only 2 keys are there, but we can't distribute into 2 nodes, 2 4s can't possible. Okay, 2 4s not possible. I can't take the 3 twos also, because if I take 3 twos, other node 1 key only left, 1 key is also not allowed. Okay, so if I take 2 4s, then 4 plus 4 8 and 4 plus 4 8, 2 2 is not allowed. Okay, so if I take 3 twos, 3 3 3, 6 6, okay, plus 4, that is already covered. Other possibility, okay, so 1 3 if we consider, okay, if one node only 3 keys, okay, if one node only 3 keys, okay, so one node is 2 keys, 3 plus 2 5 is over, and one node is 3 keys. Okay, so then one node is 2 keys is also covers here, 2 twos and 3 twos, 2 threes, similar to the previous one. So these are the 2 possible distributions, right? So this way if you distribute, so 4 values, 4 factorial, divide by 3 times 2 repeated, divide by 3 factorial. Okay, so that means this is 4 ways only. What are those 4 ways? Okay, so 2 2 2, last one is 4, 2 2 4 2, then otherwise 2 4 2 2, otherwise 4 2 2 2. Okay, so this one, this way if you distribute, okay, 4 factorial divide by 2 repeated 2 times 2 factorial, 3 repeated 2 times 2 factorial. These are 6 ways, 4C2. Okay, 6 ways. Right? Now, this is the way to distribute, okay, 10 keys into the 4 leaf nodes such that minimum 2 keys and maximum 4 keys. Okay, these are the things, possibilities. Other possibility, distribute into 5 leaf nodes. Distribute into 5 leaf nodes. Okay, so that means one way to distribute into 5 leaf nodes. One way to distribute 2 2 2 2 2, because exactly 10 keys are there. This is one way only. Okay, this structure is one way. These are the different ways we can distribute for each of the tree. Different ways we can distribute each of the tree, this 10 keys in the leaf level. Okay, so 3 plus 3, 6 plus 4, 10 plus 6, okay, so 16 plus 1, 17 ways. Okay, 17 ways, 17 trees of left biasing, because beat plus tree can be left biased or right biased. 17 trees of left biasing and 17 trees of right biasing. Okay, that means multiplication of 2, because left and right biasing. So total 34, okay, B plus trees possible. 34 B plus trees possible for these given 10 keys, okay, for given 10 keys and order P equal to 5, for given 10 keys and order P equal to 5, 34 different B plus trees are possible. Out of 34, 17 left biasing trees and 17 right biasing trees, like this one. Okay, in this structure, okay, 6 trees of left biasing, 6 trees of right biasing. In this structure, okay, 10 trees of left biasing, 10 trees of right biasing. In this structure, 1 tree of left biasing, 1 tree of right biasing, right? So answer to this given question is 34. See this question. Consider relation R with 1000 tuples, relation R with 1000 tuples and relation S with 5000 tuples. Okay, the size of block 200 tuples per block. Okay, so not given separately for R relation and S relation. So that means even for R relation also the block factor 200 records, and S relation also block factor 200 records should be assumed like that. Generally, two separate tables means block factors can be separate. Okay, but only one information given means same block factor you can consider for R relation and S relation. Okay, is it clear? Now, these two relations have to be joined as per specific join condition. Okay, as per specific join condition that need to be evaluated every pair of two relations. Okay, the memory buffer space available can hold exactly one block of for R and one block for S simultaneously at any point of time. Okay, the optimal number of block transfers required in case of nested loop join. The question, if you go for nested loop join with main memory limitation of 2 blocks to store R and S records, with main memory limitation of 2 blocks to store R and S records to perform the join. Okay, so what is number of block transfer required? Block transfer means access cost. Okay, number of blocks we need to retrieve from disk to main memory, access cost, or we can say IO cost. Okay, to perform join by using nested loop join algorithm. Okay, so only 2 blocks of the main memory space, okay, only 2 blocks of the main memory space is allocated to store R records and S records like this. Okay, only 2 blocks is allocated. This is the main memory space to store R and S records to perform the join. Okay, and total file in the disk. Okay, total this file is in the disk. Okay, first relation are 1000 tuples. First relation are 1000 tuples. One block can accommodate 200 tuples. One block can accommodate 200 tuples. It means it required 5 blocks. Okay, the R block, this R relation 5 blocks. Okay, let's say this is B1, B2, B3, B4 and B5. Only 5 blocks is required. Okay, and what about second relation? So 5000, S is 5000 tuples. 5000 tuples, each block can accommodate 200 records. Okay, so that means 25, right? 25 blocks. 25 blocks of the S records. That means this is B1, B2, B3, B4 up to so on B25. And like this 1000 records in first relation, 1000 records in first relation, assume R1 to R200 in first block, record 2012 to 400 till 400 is second block. Like that 1000 records is in the first relation. Okay, second relation 5000 records. Let's assume that S1, S2 up to so on S200, okay, till S5000. Okay, so nested loop join means each block of R records, each block of R record has to be joined with, okay, all the records of the S relation. Okay, if R is outer relation, okay, one block of R data retrieved to the main memory, so that R1 to R200 in main memory, 200 records in the same block. Okay, so one block of S records is retrieved to main memory, so that S1 to S200 in the main memory. Okay, now the join for each record of R relation with all the records of S relation, like this, all the records is done. After that, next block required B2, because only 2 blocks is used, replace with the B1, B3, B4, B5 up to so on B25, B25. So means total 5000 record is also completed join. Okay, so total 25 block access required, okay, to complete one record join. Again for second record join, 25 block access, okay, up to so on 1000 records in the outer relation. It means that 1000 times this 25 blocks retrieved, 1000 times this 25 blocks retrieved, plus, okay, these 5 blocks of the R relation, one block B1, after that B2, after that B3, those 5 blocks retrieved only one time. Okay, so 5 block access cost. This is R join S access cost. Okay, this is the R join S access cost. Okay, so it is, so 25,000 plus 5. Okay, 25,000 plus 5, 25,005 blocks access. He is asking optimal cost by using nested loop join. Optimal cost by using nested loop join. Optimization algorithm is nested loop only. Okay, I can't change the block nested loop to solve this problem, because he is given nested loop join only. But what else we can do? We can change order of the relation. If you do S join R, then it become reverse way. Okay, what is reverse way? 5000 times this 5 block has to be accessed. Okay, 5000 times 5 block access required, plus now outer relation become 25 blocks. Okay, so that means this is the outer relation. So 5000 times this inner block 5 blocks is retrieved, plus this 25 blocks of the outer relation. So that means it become 5000 and 25,000 plus 25, it is become 25,025 blocks. Okay, so still this first one only optimal. So the answer to this given question, okay, answer to this given question is 25,000 5 blocks, 25,000 5 blocks access cost. Right, by using nested loop join. So the next immediate question, instead of using nested loop join, the same question, assume that if block nested loop join is used, okay, only the format of the algorithm is changes, same calculation. Then what is optimal access cost? Now here the difference is, okay, it's not like one record join with all the records of second relation. Okay, one block of records, okay, one block of records, B1 block of records can join all the records of B1 here. Again, R1 join with S1 to S200, R2 joins with S1 to S200, and R200 joins with S2, like this. All these B1 records can join simultaneously. Okay, so before going to the next B2 records, okay, then all the records of B1 joins with all records of this B2. All records of this B1 joins with all records of B3. Okay, like that if we join, that is called block nested loop join. Okay, if you go for block nested loop join, so anyhow, as like before, the first block we retrieved, for R relation, first block we retrieved from S relation. Okay, now not only R1 joins with S1 to S200, R1 joins with S1 to S200, R2 also joins with S1 to S200, up to so on. R200 also joins with S1 to S200. That means all these B1 blocks and all these B1 blocks completed join. After that B2 is replaces and join with all B2 records, and B3 is replaces, join with all B3 records, up to so on till B25, till B25. Okay, and so next after B1 completed join with 25 blocks, 25 blocks, then next B2 is starts, and like that up to so on till 5 blocks here. Okay, that means previously number of times this inner block access is depending on number of records of outer table. Now number of block access come from this inner relation is depending on number of blocks of the outer relation. Now R join S access cost, this 25 block access required only 5 times, not 1000 times. Okay, so 25 block access required only 5 times plus these 5 blocks. Okay, so it becomes 125 plus 5 is become 130 blocks access cost. Okay, so previously 5005 block access cost reduced to 130 block access cost just because of changing nested loop join to block nested loop join. If main memory restriction is there, this block nested loop join algorithm is reduces access cost compared to the nested loop join algorithm. If you try for changing the order to perform the access cost, okay, if outer relation is S and inner relation is R, if outer relation S and inner relation R, that means for one block of outer relation 5 blocks of inner relation, so 25 times 5 blocks. Okay, so instead of okay, 25 blocks are repeated 5 times, so 5 blocks are repeated 25 times. Okay, same, but outer cost is changes. This outer cost previously 5 blocks, this outer cost now it become 25 blocks. Okay, this is the cost of repeating inner loop and this is the cost of accessing outer loop. Okay, so that means, so 125 plus 25 is become 150 blocks. Okay, so out of these two, the 130 only optimal, right? So then answer to this given question. So R is only outer relation, so total it required 130 blocks access cost. Right? See this question from the ER model. So employee entity set, employee ID, key attribute, name. Department entity set, department ID, department name, key attribute, department ID and department name, other attribute. One relationship manages, it is one-to-many mapping, and other relationship works for, it is many-to-many mapping, and other relationship tech advisor of the department, it is one-to-one mapping. Okay, so how many minimum relational tables required for this ER diagram? So it is a standard model only, it is not a very different model question. So the reason for solving one of the standard model question, because this is very frequent in the examination. Okay, hopefully for 2024 gate, if they given some ER model question, okay, maximum possibility same, finding minimum relational tables. Okay, so before going to this question, just overview, there are 10 rules. Okay, there are 10 different rules are reduced to means 8 conditions. Okay, just see this one. Irrespective of the one-to-many mapping, either it is partial participation or total participation, either partial participation or total participation, one-to-many relationship combined with E2 entity set. this one-to-many relationship combined with E2 entity set. So these are the E1 entity set and FDs, and this is E2 relationship and E2 entity set and relationship. Foreign key added because of this one-to-many relationship, okay, which is refers to E1. Even if it is total participation, same design, and minimum 2 relational tables required, one foreign key as well as BCN of design. Okay. Now, if many-to-many relationship, so we need separate relationship for separate RDBMS table for relationship set. So then it required 3 tables. Then minimum it required 3 tables. So minimum 3 tables and 2 foreign keys. Okay. So if 1-to-1 partial participation both sides, then relationship can combine either the sides, whichever side having more participation. So that means 1-to-1, 80% participation, 40% participation. So whichever side having more participation, that is a better side to combine the relationship. So 1-to-1 relationship, okay, so can combine either E1 side or E2 side, 2 possible designs. This is one possibility and this is other possibility. Okay. So 1-to-1 with at least one total participation or both total participation can combine into single table. Okay. 1-to-1 with at least one total participation or both are total participations, okay, can combine into single table, okay. So and no foreign keys required, okay. Just practice these 4 categories of the RDBMS design: 1-to-1 design, many-to-many design, 1-to-1 partial participation both sides, 1-to-1 at least one total participation, many-to-1 and 1-to-many same. Next, even if self-referential 1-to-many can combine with the entity set. Self-referential 1-to-1 can combine with the entity set. Self-referential many-to-many relationship should be separate table. Okay. Self-referential 1-to-many minimum 1 table and 1 foreign key. Self-referential 1-to-1 minimum 1 table and 1 foreign key. Self-referential with many-to-many minimum 2 table and 2 foreign keys. And weak entity set. Okay, the other one is weak entity set. Whenever weak entity set is given, a relationship combined with the weak entity set is 1 table and E1 other side is other table. Okay, so write as like a short notes for these 8 points clearly with the what are functional dependencies, how it is BCN of what the RDBMS design in detailed I written, FD set also written and minimizer design also written and BCN of also satisfied. Okay, all are clearly written in these 8 points. Max to max, okay, of ER model question should be related to this topic only. Okay, so now back to the question. 1-to-many can combine with many side. 1-to-many can combine with many side entity set. Many-to-many relationship should be separate table. And 1-to-1 partial participation both sides. The entity can combine either the sides. Okay. So more participation at the department side because less departments than the number of employees. This is right side. Okay. That means overall the RDBMS design is become like this. Overall RDBMS design is become like this. Okay. So 1-to-many relationship combined with the department set and tech advisor also combined with the department set. Okay. This is one RDBMS table. This many-to-many relationship should maintain separate table and this is separate table. Okay. So minimum 3 relational tables required. So 1-to-many combined with the department set. One foreign key refers to EID. Okay. And this is separately maintained. One foreign key refers to EID and one foreign key refers to this DID. 2 foreign keys required for this. Okay. And so tech advisor 1-to-1 combined with the department side. For this, 1 foreign key required. 1 foreign key for managers relation, 1 foreign key for tech advisor and 2 foreign keys for works for relation. So that total it required 4 foreign keys. Okay. So got it. So the detailed explanation how 1-to-many designed and how many-to-many designed, how 1-to-1 total participation or partial participation is designed is given in detail notes here. Okay. So 1-to-many combined with the right side. Okay. Many-to-many should maintain separate table. 1-to-1 partial participation can combine with either the sides. 1-to-1 at least one total participation can combine with Okay, any of these entities can combine together with no foreign keys. Okay, so and self-referential also similar design. Okay, self-referential one to many. Okay, self-referential one to many. Okay, this is the design. Self-referential one to one, this is the design. Self-referential many to many, this is the design. And this is the weak entity set. E1 strong entity set, E2 is weak entity set. Okay, relationship is weak relationship. Relationship and weak entity set should be one table, E1 is other table. These are the 10 points related to the ER model. Okay, so 99% of ER model question should be based on this topic only. So practice these 8 points properly, right? See this question. This is the question related to the transaction management, and the question related to the conflict equality and precedence graph. Okay, so before which of the following statements are correct? Okay, which of the following statements are correct? Okay, is the question. So S1, S2 schedules over same transactions. Assume that S1, S2, two schedules, both are involved with the same transactions. Whatever transactions involved in the schedule S1, same transaction, same set of transactions for S2 also. Okay, if S1, S2 schedules with same precedence graph, their precedence graph is same. Okay, then the schedules are conflict equal, true or false. If conflict equal is true, then both must have same precedence graph. Okay, if same precedence graph and acyclic precedence graph, then should be conflict equal. Okay, and same precedence graph and cyclic precedence graph, then also conflict equal. Like 4 statements is given, we need to see which is correct and which is wrong. Okay, so try this question first before going explanation. Now let us see what is mean by conflict equality. Okay, so by two schedules are conflict equal if and only if by swapping okay, adjacent non-conflict pairs of one schedule. Okay, because of swapping adjacent non-conflict pairs of S1, if S2 is derived, then we call conflict equal. So other way to say conflict equal, both the schedule must have same set of transactions, okay, and every conflict pair precedence of both the schedules must be same. Then we can say conflict equal schedules. Okay, by keep on swapping adjacent non-conflict pairs of the one schedule, if we able to generate the second schedule, then also conflict equal. If both the transactions with same set of both the schedules with same set of transactions and both the schedules with same conflict pair precedences, every conflict pair of the first schedule same precedence in the second schedule also, then conflict equal. Both are equivalent definitions, right? So these are the common observations or conclusions we can observe. If you prove conflict equal means all the conflict pairs are same precedence with same set of transactions. Anyhow, same set of transactions, default assumption. If any transaction of two schedules is not same, assume T1 transaction of the first schedule, T1 transaction of the second schedule, if not same, there is no meaning to compare the schedules. So we are comparing schedules means both the schedules should have the same set of transactions. If some transaction is not same, okay, so guaranteed conflict equality not true, right? Now same set of transactions is one important thing, and conflict equal means all conflict pair same precedence. Conflict pair only adjacent in the precedence graph, then it's going to be the same precedence graph. Okay, the schedules with not same precedence graph is not same, okay, then guaranteed not conflict equal. Conflict equal means same precedence graph, okay, not same precedence graph, some edge in the precedence graph not same, means some conflict pair not same precedence, means it is not conflict equal. Okay, and third one, same precedence graph and cyclic precedence graph, okay, then may not be conflict equal. This is the one of the failure case to prove conflict equality by using the precedence graph. In case precedence graphs are same, okay, precedence graphs are not same, no problem, not a conflict equal. But precedence graphs are same and having cycle in the precedence graph, then may not be conflict equal. This is the example. Okay, this conflict pair not same precedence, this conflict pair not same precedence. So both are not conflict equal. S1, S2 not conflict equal. Okay, so but both are having same precedence graph. For example, if you draw precedence graph for first schedule, because of this conflict pair T1 precede then T2, because of this conflict pair T2 precede then T1. Here also, so if you draw precedence graph, okay, if you draw precedence graph T1, T2 and T2 to T1. So same precedence graph and cyclic precedence graph. In that case, it may not be conflict equal. Okay, but if the precedence graph is same and precedence graph is acyclic, same precedence graph and acyclic precedence graph, then it is a conflict equal schedule. Okay, so when conflict equality can be true by using precedence graph should be same and acyclic precedence graph, then schedules are conflict equal. It means, so for example, okay, this statement simply says that not every time, okay, we can able to test conflict equality by using precedence graph. The failure case is this one. Okay, this is the failure case. Even precedence graph is same. Okay, even precedence graph is same. Sometime conflict equality can fail. Sometime conflict equality can fail. But what are the cases we can conclude? Okay, if precedence graph some edge is not same, precedence graph some edge is not same, that means precedence graph not equal. Okay, if precedence graph not equal, then not conflict equal. Precedence graph not equal, then not conflict equal. Same precedence graph, okay, precedence graph equal and acyclic. Precedence graph equal and acyclic, then guaranteed conflict equal. Okay, but precedence graph equal but cyclic. Okay, precedence graph equal but cyclic, may not conflict equal. Okay, this is the three main important things you can understand. Okay, conflict equality testing versus precedence graph comparison. Okay, now back to the question. So what we say is that schedules same transaction, first option A, same precedence graph. Okay, so precedence graph of schedule is equal, then we can say conflict equal. Okay, is false statement. Okay, this is the false statement, because same precedence graph, okay, need not be acyclic, it can be cyclic also. Say even precedence graph is same, if it is cyclic precedence graph, okay, then it may not be conflict equal. Okay, that is a third case in the diagram we discussed. Okay, if conflict equal already true, guaranteed same precedence graph. Okay, this is a true statement. If conflict equality itself is true, then precedence graph guaranteed same. Now the third one, same precedence graph and acyclic precedence graph. Two schedules, same precedence graph and acyclic precedence graph, then guaranteed conflict equal. This is also true statement. Okay, now same precedence graph but having cycle. Same precedence graph but having cycle, it may not be conflict equal. This is a false statement. Okay, so all these explanation and so answer to this question is BC. Okay, so B and C is the correct statements. Okay, so detailed explanation and short notes related to this topic. Detailed explanation and short notes related to this topic. What is mean by conflict equal, we discussed here, and what are conclusions, what are comparisons between conflict equality versus and precedence graph comparison. Okay, so 4 statements I written, and those 4 statements explained in 3 cases. Okay, so this is one other important model from the DBMS, right? See one more question related to transaction and concurrency control, that too conflict serializability relation, conflict serializability topic related question. Okay, schedule is given. So W1X, R2A, R3A and W1B and W2B and W3B, and how many So how many serial schedules are conflict equal to the given schedule? How many serial schedules are conflict equal to the given schedule? Okay, so is the first question. And the second question, how many, not only serial schedule, first one is only related to the serial schedule. So how many serial schedules? So how many serial schedules conflict equal to the given schedule? The second one, how many schedules conflict equal to the given schedule? Okay, first one is only related to the serials conflict equal to the given schedule, and second one, total possible schedules which are conflict equal to the given schedule. Okay. Now for this first question, number of serial schedules which are conflict equal to the given schedule is number of topological orders of the precedence graph. Okay. So the number of serial schedules which are conflict equal to given schedule, number of serial schedules conflict equal to given schedule, conflict equal to schedule S is equal to number of topological orders, number of topological orders of schedule S precedence graph. Okay, this is one an important statement. Okay, may be useful for theoretical questions also. Okay, the topological order gives the total possible serial schedules which are conflict equal. Serial schedules which are conflict equal is the number of topological orders. Okay, so for this we need to compute the topological orders, means precedence graph construction required. So 3 transactions in the schedule, 3 vertices in the precedence graph, W1A R2A one conflict pair, W1A R3A is one conflict pair, that means T2 to T3, T1 to T2, right? T1 to T2, T1 to T3. Okay, so T1 to T2 and T1 to T3, these two. And W1B precede then W2B and W3B, that is T1 to T2, T2 to T1 to T3, and W2B precede then W3B is also conflict pair. So this is the precedence graph. The precedence graph is acyclic, means it is conflict serializable schedule only, and topological order. How many topological orders are there? T1 in degree 0, then after removing T1, T2 in degree 0 and T3. Only one topological order. One topological order means only one serial schedule. Okay, only one serial schedule, conflict equal to S. Conflict equal to the schedule S. This first question answer is 1. One serial schedule only, T1 followed by T2 followed by T3 serial order, conflict equal to the given schedule. And the second question, interesting thing, okay, how many total schedules which are conflict equal? Okay, without affecting conflict equality, total how many schedules are possible? So conflict equal means, okay, conflict pairs must be same precedence. Okay, conflict pairs must same precedence, must be same precedence, and operations of the transactions must be same. Okay, transactions of S1, S2 must be exactly same. Okay, so transaction sequence should not affect, operations of the same transaction sequence should not affect, and all conflict pairs should maintain same order, same precedence order. Okay, then we can say conflict equal. Okay, without affecting this, how many different possible ways, okay, we can reorder these operations. Okay, how many conflict equal schedules for this given schedule? I am just writing the given schedule. Okay, this is the given schedule. So in this given schedule, whenever means say to formulate the conflict equal schedule, okay, you should take care this conflict pair must be same precedence. Okay, after W1A, R2A should be there. After W1A, R3A should be there. Okay, this conflict pair should not affect. Similarly, after W1B, W2B there. After W1B, W3B should be there. After W2B, W3B should be there. These are the conflict pairs. These conflict pairs should not change their precedence. And the operations of same transaction, W1B must before the W1B, W1A must before the W1B, T2, R1A must before the W2B, and R3A must before the W3B, because transactions of both the schedules should be same. Okay, so let's formulate the possibilities. So see these three conflict pairs, because of first second also conflict pair, second third also conflict pair, first third also conflict pair. So because of three conflict pairs, so not allowed to change any two conflict pairs, right? Okay, so that means this W1B, W2B, W3B must be same precedence. This W1B and W2B and W3B must be same precedence. If you change any of these two operation, the conflict equality condition, because we are expecting conflict equal, means this precedence of conflict, this W1B precede then W2B, 2 precede then W2B precede then W3B, 1 precede then W3B, and these things should not affected. Now after that remaining operations are there, and operations of same transaction also must be same order. So this according to these three rights, W1B we written first. Okay, so before W1B only we should write the W1A. Okay, because those are related to same transaction. So W1A only have this position. Okay, so operations of same transaction. So transactions of S1. So S1 W1A before W1B. In this conflict equality also W1A before W1B, right? Next R2A is there, right? R2A is there. What is restriction for R2A? R2A and must execute before the W2B because both are related to same transaction. Okay, both are related to same transaction. This sequence should not affected. Okay, transaction T2 sequence should not affected. R2A should be before W2B, and this conflict pair for R2A should not affected because of this conflict pair with W1A. So R2A should be after W1B only. That means R2A should be after W1A because of conflict pair W1A R2A, and it should be before W2B. Okay, because operations of T2 should be in the same order. Transaction sequence should not affect. Means there are two choices for R2A. Okay, so R2A can be placed after second position here, or R2A can be placed at third position here, but it should not go beyond it. If you go beyond it, the transactions of S1, S2, the transactions of given schedule and transactions of this conflict equal schedule is get violated. Okay, that means after placing R2A, we got the two schedules. Okay, so let me write those two schedules to avoid the confusion. Okay, so these remaining operations as it is. Okay, these remaining operations as it is. Only difference is that R2A. So R2A can come second position, means after W1A. Otherwise R2A can come in the third position after W1B. So R2A can be either here. See this conflict pair same precedence, and R2A can be either here. Okay, so conflict pair not violated, R2A before W2B. This conflict pair precedence not violated, R2A before W2B. Two possibilities. Okay. Next, same conditions for R3A. R3A must before the W3A because operations of same transaction must be same, and conflict pair precedence should be same. Means R3A also a conflict pair with W1A. So R3A should be after W1A, and R3A should execute before W3B. Okay, because the operations of same transaction must be in the same order. So if you think both these conditions, what are possibilities for R3A? Okay, possibilities for R3A. R3A can't be first position. Okay, R3A can't be first position. R3A can be second position, or R3A can be third position, or R3A can be this fourth position, and R3A can be this fifth position. Okay, these are the different possible places where R2A can be accommodate. Okay, it should be before W3B and it should be after W1A. After W1A because of conflict pair, before W3B because of same transaction. So these are the 4 conflict equal schedules. Similarly, again for the second schedule, okay, this R3A for the second schedule. So R3A can be placed in the second position, in the third position, or in the fourth position, or in the fifth position. Okay, because R3A must be W1A must precede then R3A. So R3A can't be in the first position. W1A is already conflict pair with R3A where W1A is preceded, and R3A not go beyond the W3B. So these are the 4 more possibilities. So total 8 schedules which are conflict equal, including this given schedule. Including this given schedule, 8 schedules are conflict equal. So he is asking how many schedules are conflict equal, means the equal to the given schedule is also one of the schedule. Okay. For example, if they say how many other schedules which are conflict equal to the given schedule, then out of this 8 you should exclude one of them, because this given schedule is also one of the schedule out among this 8. Okay, but he is not asking to exclude this also. So you can include the given schedule also conflict equal to itself. Okay, so answer to this second question, 8 conflict equal schedules. Okay, one serial schedule only which is conflict equal, but 8 concurrent schedules which are conflict equal to the given schedule. Okay, so in case if they ask how many other schedules which are conflict equal to given schedule, then we can say 7, because out of this 8 you can observe this is also one of the schedule. This given schedule is also one of the schedule out of these 8 schedules, right? But whenever they say simply conflict equal schedule, we will not exclude the given schedule. Okay, given schedule also considered as one of the schedule for conflict equality, right? So answer to the second question is 8. Similar to the second question, we need to compute the view equal serial schedule. View equal serial schedule. The how many serial schedules which are view equal to the given schedule. Okay, that means without violating view equality condition, initial reads of both the schedules should be same. Okay, updated reads of both the schedules must be same, and final writes of both the schedules must be same. Without affecting initial read, updated read, final write. Okay, how many serials which are view equal to the given schedule? Okay, see, 3 transactions are writing the data. So final write must be done by the T3. Final write must be done by the T3. So final write must be done by the T3 means according to this B. So final write should be done by T3. Okay, that means the previous 2 write operations can be any order. Okay, previous T1 write operation and T2 write operation can be interchangeable. Okay, so this is the sequence according to final write. Next, initial read. Initial reads are not there because after W1A, T2 and T3 is reading. Because of this updated read and because of this updated read, okay, in equal serial order, T1 should before T2 and T1 should before T3. Okay, so that means T1 must be before, okay, T2. Then T2 in updated read from the T1, and T1 also must before the T3. T1 also must before the T3 because of this updated read. T3 also should read T1 updated data. T2 also should read T1 updated data. T2 reading T1 updated data, T3 reading T1 updated data. So these are the two conditions. These are the conditions to satisfy view equal serial order. So view equal serial order, overall we say T1 must before T2, T1 must before T2 and T2 must before T3, right? So again one view equal serial only, okay, that is T1, T2, T3. Because of this initial read, because of this updated read, okay, because of this updated read, okay, T1 must before T2 and T1 must before T3. Because of this final write, T1, T2 can before T3, okay. So that means one serial schedule, okay, one serial schedule view equal to the given schedule. Only one serial schedule which is view equal to the given schedule. So the answer to this first question is 1. One serial conflict equal also, one serial view equal also, okay. Then the second one, the how many schedules may not be serial, okay, how many concurrent schedules which are view equal to the given schedule, means without affecting view equal condition, without affecting view equal condition, we should formulate all possible serial orders, all possible schedules, may not be serial order only, all possible schedules which are view equal. I am just writing this given schedule for reference purpose, okay. So this is the given schedule. So for this given schedule, we need to formulate the every possibility of view equal schedule, okay. Every possibility of view equal schedule may not be serial, okay. So this is serial schedules which are view equal. Now every possibility of the schedule which is view equal to the given schedule, okay. Now, so these two write operations can execute any order because final write should be done by the T3, okay. This is the final write. Final write of B done by the T3. This T1 and T2 write operations can be any order. That means, so W1B, after that W2B and after that W3B is also view equal, okay. So the other possible choice, W2B can execute before W2B and then after W2B, then next one is W1B, then final write is W3B, okay. This is also okay. So these two writes can be any order, right? Now, so first operation is W1B, okay. See, because operations of the same transaction must execute same order, because of that reason W1A can be only in the first position, not because of the final write and those things are get affected. Operations of same transaction must maintain same sequence. Now this R2A, this is updated read from the T1, and this updated read from the T1 means the R2A can't go before the W1B, okay, because of updated read. So because, and R2A can't come after the W2B because of same transaction operations, okay. So that means R2A can accommodate in the second position or in this third position, okay. R2A can be stored, R2A can be placed in the second position or in the third position without affecting view equality and without affecting operations of same transaction in the same sequence. So let's rewrite. So to understand more better way to possibilities for R3A. Two choices we got for R2A in this first sequence, okay. That means W1A anyhow first, after that R2A can be in the second position, then followed by W1B and W2B and W3B. This is W3B, okay. Other possibility, so W1A in first position, W1A, after that W1B, then R2A, followed by W2B. Operations of same transaction should not get affected. That's why we are not able to move this R2A to the after W2B position, right. So these are the two choices left. These are the two choices left in this first sequence. Okay, so after that only one operation left, which is R3A. Again same thing, R3A updated read should not affected. Updated read must be maintained same order. Because of updated read, R3A should be after W1A only. After W1A only. And operations of same transaction must be same sequence. R3A must before the W3A. So in this way, so R3A can be accommodate here and here and here and here. 4 possibilities. Okay. And R3A can accommodate here or here, here and here is also 4 possibilities. These are 8 view equal schedules. These 8 view equal schedules is also conflict equal schedules. These 8 conflict equal schedules itself is the 8 view equal schedule, because conflict equality is true, is guaranteed view equality is also true. Conflict equality true, guaranteed view equality also true. Now, but so first 2 right B's can be interchangeable. First 2 right B's can be interchangeable because final write is done by T3. If you take this sequence, the first operation is W2B and R2B must be before W2B. R2B should be here only. R2B or A. R2A should be in the first position. Next if you think about R1A, okay, W1A, not R1A, this one, W1A. Next, think about the W1A possibilities. Okay, see, W1A also must be the only first position. The reason is it should be updated read. T2 should read T1 updated value. Because of this updated read, W1A also should be here only. Because of same transaction, R2A can't be after this W2B, R2A should before the W2B, R2A should before the W2B because of same transaction, and because of this updated read, okay, R2A should be after W1A. That means R2A after W1A means W1A should be in the first position. Okay, now R3A is the other operation. What is conditions? R3A should be before W3A because of same transaction, and R3A should be updated read from W1A. Okay, R3A can't be first position, because if it is first position, the R3A not become updated read, become initial read because of updated read condition. Okay, so because of updated read condition, R3A should be after W1A, and R3A can be here also. Still updated read not violated, and R3A can be here also, still updated read not violated, T3 operation sequence not violated. R3A can be here also because these are right B's. Okay, so even if R3A is here, still T3 is reading T1 updated value, but R3A can't be after W3A because, okay, in the given schedule R3A is given before W3B. Okay, so now these are the 4 ways. So total 12 view equal schedules. Out of these 12 view equal schedules, okay, this given schedule is also one of them. But it's simply asking how many schedules view equal. In that case, we should not exclude the given schedule. Given schedule also part of it. Okay, so see, so whatever we got conflict equal schedules, 8 conflict equal schedules, those 8 conflict equal schedules is also view equal schedules, and extra 4 schedules which is also view equal, this extra 4 schedules which is also view equal but not conflict equal. Okay, so got it. So the second question, all possible schedules which are view equal, is 12 schedules which are view equal. Okay, this is the way we need to, okay, so compute number of conflict equal serial schedules, number of view equal serial schedules, number of view equal schedules. Similarly, number of conflict equal serial schedules, number of, okay, schedules which are conflict equal. Okay, so very closest terms. Okay, here we are finding serial schedules conflict equal, every possible schedule conflict equal, both are different meaning. Similarly, serial schedules view equal and all schedules view equal, both are different meaning. Okay, so this is other important, very important model question for GATE examination, conflict serializability as well as view serializability, right? See this question, which of the following statement is are true? Okay, first one, conflict serializable schedule testing condition, conflict serializable schedule testing condition, conflict serializable schedule testing condition is only sufficient but not necessary condition for serializability testing. Okay, and conflict serializable schedule testing condition is both sufficient and necessary for serializability testing. Okay, so conflict serializability testing is NPC problem, view serializability testing NPC problem. Okay, so now let us see the expressive power diagram related to the conflict serialization and view serialization and overall serializability. See expressive power diagram of conflict serialization. So now see serial schedules, next conflict serializable schedule superset of serial, means every serial is conflict serializable. Conflict serializable schedule may be some non-serial also. Okay, so every conflict serializable is view serializable. Schedule is not view serializable. It can be a non-serializable schedule, means concurrent schedule is the superset of view serialization. Okay, so either it is conflict serializability or view serializability. Either it is conflict serializability or view serializability. Overall, we can say schedule is serializable. Okay, if the schedule is satisfied conflict serialization, okay, conflict serializability acyclic precedence graph condition true, then guaranteed schedule is serializable. Okay, but schedule is not satisfied conflict serialization. It may be serializable because of view serializability or may not be serializable. It means that if conflict serializable schedule testing condition true, conflict serializable schedule testing condition true, then guaranteed schedule is serializable. Okay, then guaranteed implied schedule is serializable, but conflict serializable schedule testing condition false, it may or may not serializable. Okay, such a conditions are called only sufficient but not necessary. Because conflict serializability true, it's a serializable. Conflict serializability if not true, it may or may not serializable. Such a conditions are called only sufficient but not necessary. Okay, but when it comes to view serializability, okay, so when it comes to view serializability, if view serializability testing conditions are true, okay, these are the view serializable, these are all view serializable schedules. Okay, these are all view serializable schedules. Okay, which includes conflict serialization, and some are may not be conflict serializable, still it can be view serializable. If view serializability is satisfied, then it is a serializable. If view serializability fails, then non-serializable. If view serializable schedule testing condition true, then it is a serializable schedule. View serializable schedule testing condition false, then it is a non-serializable schedule. Such a conditions are called both sufficient and necessary. Okay, so then conclusion is conflict serializable schedule testing condition acyclic precedence graph or not is only sufficient but not necessary condition for serializability conclusion. Okay, but view serializable schedule testing condition is both sufficient and necessary for serializability conclusion, right? So first condition, first statement he says that conflict serializable schedule testing condition only sufficient not necessary for serializability is the true statement. Okay, conflict serializable schedule testing condition both sufficient and necessary condition, both sufficient and necessary condition, okay, is not true statement. Okay, this is false statement, right? Now, so this is about the expressive power of the conflict serialization and view serialization. Then the schedule conflict serializable or not. Okay, the schedule conflict serializable or not. Assume that conflict serializable condition testing. Okay, condition testing. Conflict serializable condition is draw the precedence graph, check the precedence graph acyclic or cyclic, is polynomial time complexity problem, P problem, polynomial time complexity problem, the time complexity of that is, okay, worst case is n square, okay, for n transactions, okay. So, worst case n square for n transactions, right. So, because only acyclic precedence graph or not, that is it. Construct precedence graph, is it acyclic or not? Precedence graph acyclic or not? It required only polynomial time. So, conflict serializability testing is NP complete problem is false. NP complete means exponential time complexity by using deterministic algorithm, okay. But view serializability testing conditions, okay, view serializable or not, view serializable testing condition, schedule is view serializable or not, the testing is exponential time complexity, NP complete problem, NP complete problem, okay. So, it required exponential time complexity, exponential time complexity, this is polynomial time complexity for conflict serialization. So, view serializability testing is NPC problem, view serializable testing is NPC problem is a true statement, okay. So, this is one other good conclusion related to conflict serializability and view serializability, okay. So, this is all about GTQ program of DBMS for GATE 2024, and also 2021 GATE one YouTube video is there for GTQ program 2022, 2023, and this is the fourth video, okay. Just go through all 4 videos, almost you will get the maximum practice and maximum good questions and quality questions for GATE 2024 for computer science as well as DA, okay. So, it is available in YouTube, okay. Last 4 years means last 3 years plus this one, 4 years, 4 videos, okay. So, each video approximately more than 15-16 questions, okay. So, it covers every area, every important area and most quality questions and detailed explanation, okay. So, this is all about the today's GTQ video, and all the very best for your upcoming GATE examination. Hope you are all going to do well, and whatever you prepared, just keep revise, and okay. So, don't do much test series and all in last 3-4 days or last 4-5 days. Stop writing the test series, okay. Stop giving the test series means at least 3-4 days before, okay. Before that means 1 week before or 5 days before you should give the test series obviously, okay. So, please revise and don't touch any new things, okay, new topics and unknown topics at that last moment, okay. So, all the very best, and lot of admissions are there for MTech, especially computer science, okay. So, even only IISc and IIT Mumbai more than 250 admissions, okay, in total. Only 2 colleges, okay, that too. So, that means, okay, even if you get 300, 400 rank, or okay, maybe a chance to get the top 1-2 college, okay. So, just imagine like 23 IITs are there, and lot of NITs are also very good, okay, and lot of triple IITs also there, and lot of good universities like Jadavpur, DTU, etc., okay. So, lot of admissions are there for computer science, more than 45-50 top colleges where average package for MTech computer science is more than 20-25 lakh CTC, okay, as a fresher. So, and every college out of that 45-50 college, computer science, engineering, MTech, and information security and data science and artificial intelligence or software engineering, like 4-5 streams also, okay. So, every college at least 3 streams are there for computer science related, means even you get 3,500 until 4,500 rank, till you will get the very good college for MTech admission, especially a computer science. Okay, so even 4000 rank is still, you have a very good chances to move forward in computer science through your MTech computer science from the one of the good college in India. Okay, where you will get easily 20 lakh plus CTC job. Okay, so there is no need to stress much, and very best possible options are available once you clear the GATE examination, and your complete means a, we can say, life turning point before GATE and after GATE kind of thing you can see if you are done good in GATE examination. Okay, no need to stress, because it is not like only 200 admissions or 300 admissions only. So more than 4000, 4500 good MTech admissions, and you will also get lot of non-GATE options also. Okay, so if you have any query, you can mail me, or you can contact through Made Easy Telegram group. So I will try my best to give best possible suggestion to you. All the very best, and so keep doing your best and be calm and stay focused for the examination. Okay, thank you everyone for all your support. Take care.